Okay, hello everybody. My name is Andrea Malchiodi and I'm the current director of the Georgi Mathematical Research Center. So I would like to welcome everybody to the workshop Statistical and Computational Aspects of Dynamics. I will just say a few words about the Georgi Center and promise I won't take much of your time. So the center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, but with the mission of being a center for the whole mathematical community in Pisa. So which includes mostly colleagues from the University of Pisa and also from Scuola Superiore Sant'Anna. So these institutions, especially the former, contribute financially and crucially to the activities of the center. So those activities since the foundations have been mainly workshops, schools, and intensive research periods. And we also started recently a colloquium series. We have visiting positions of two types. So there are short-term visiting positions to perform research in pairs, and also 2 years postdoctoral positions. So as many centers of these types, we were affected strongly by the pandemic. Luckily, last year, we were able to restart almost normally. So there was a short break in winter. Hopefully, everything will go smoothly this year. And finally, I just would like to conclude thanking the organizers for bringing up this very nice event, and also the staff of the center for very valuable and constant support. Thank you.
Good morning, everybody. I would like to first introduce myself. My name is Tanja Schindler. I'm one of the organizers. Well, I should first thank my co-organizers. There is Casun Fernando. Just stand up so people can see whom they should ask if there's some trouble. There is Paolo Giulietti. So if everything doesn't go as smoothly as we hope it should go, then please contact any of us. And yeah, I don't want to say too much. I'm very happy we can be here. I was a postdoc myself here, basically during COVID time. And so it's a pleasure for me to come back to normal times and have this conference here. And I'm very grateful for the center to give us the opportunity to have this workshop here. And well, I also want to thank all the speakers who responded very quickly to come to Pisa. And yeah, I wanted to open the session with a mini course by Caroline Worrell. Come up, and she is talking about numerical estimation in chaos. And do you need any help setting up, or we? Okay, I think the stage is yours.
Great, thanks.
Do you need one of these microphones?
Okay.
This one.
We'll see. Okay, thank you. Well, yes, I suppose first. Yes, so I suppose firstly, thanks to the organizers for having me here and for putting on this workshop that will hopefully be very nice, and we'll all have a good time and learn some things. So this I suppose this mini course is going to be a numerical course, and well, I suppose when I was asked to do this, Casun was like, you know, can you make it as I suppose as applied as possible, or very applied or whatever. So I suppose what I would like to do here is to talk about some let's say chaos in its. Talk about some numerics that can handle a very general set of chaotic systems. There's particularly ones that don't necessarily put too much structure on the, you know, the geometry of these systems, because these are, you know, we like to study systems with a lot of geometry, and this makes everything very nice for us, particularly if we want to know everything about a system and like not have any uncertainty that what we're doing is not all for nothing, is not wrong. So somehow, you know, going outside of that requires perhaps a bit of understanding what we don't know, and what needs to, and sort of maybe trying to restrict that to some extent, but still not using the usual kinds of ways that we like to restrict what we don't know. Perhaps having to do some kind of, probabilistic estimates. So the first, I suppose, lecture is going to be perhaps a little bit philosophical, trying to motivate why we're doing numerics, but then also to sort of, go through some basic ideas about chaotic systems and how that kind of affects what we do when we do computations. And then I'll talk a bit about, well, I suppose sort of, probabilistic sampling of chaotic systems, and then the things that really will be the meat. One of the most important things that you can ideas in numerical chaos is perhaps coming out of it being a very important idea in sort of mathematical proof type chaos, which are sort of transfer operator estimation, and then this will tell us a lot about our system. Well, yeah, this is sort of let's say the meat and potatoes of what a lot of people do in chaos. So yes, so this first lecture, as I said, will contain some ideas. And okay, so to begin with, I should say, why numerics? Why do we want to use numerics? I suppose if you're going to sit here and listen to me for however long, you want to understand this. You sort of want a reason to do that. And well, I suppose somehow numerics are really, so that is, using your computer to perform some calculations is somehow just an automation of using pen and paper and your hand and your brain to perform calculations. And well, this is something that everyone does everyone does in mathematics. When you prove a theorem, often you have to, compute some bounds or something like this. Well, a computer somehow is just and sometimes perhaps you even want to find some quite specific numbers, particularly if you're not proving a theorem. If you're just trying to see if something works, you take a particular example, you say, okay, well, like, can I just, I don't know, see if this example has the properties that I want. And often typically what you're doing there is you're trying to, you pull it apart and you try and see if, I don't know, if you're an analyst, see if some numbers go to zero as you increase something. Perhaps if you're more algebraic, maybe you try and look at specific examples of a group or something. But furthermore, even outside of being a very pure mathematical thing, I'm not sure what the sort of background of everyone here is. But if you are actually interested in actual systems, as they, like something, in real world, some fluid flows or something, then somehow you're doing calculations for a specific system because, you want to get a particular number out, for example. You may not necessarily, like you just have to, add some numbers together or something like this. So, in the real world, not in the real world, in the sort of set of scientific endeavor, mostly, in fact, what we use computers for is in this top percentage here. So we have some system that we care about. We actually care about this system in and of itself, not just in the sense of advancing something, some bigger mathematical idea, and we want to compute it, get a number. But in the world of mathematics, we sort of have, we have these two other things, which is trying to see whether a result is, whether, something we want to prove is true. I use an example, and perhaps even sometimes we use it to prove a theorem, by which I mean a computer, sorry, we use a computer to prove a theorem rather than just doing it by hand. Yeah. So, the history of a computer is that, which is probably something you've probably all seen before, but I will just tell you, computers originally were people. You needed to integrate something, run an ODE for a very long time or something like this. And you got if you couldn't be bothered doing it yourself, you got someone else to do it. And here is a picture of some computers at NASA, who, as you can see, were all women, because I suppose at some level, this is some kind of secretarial, it was considered some sort of secretarial work. But not long after they sort of computers started being viable for use. And so you started getting, eventually you ended up with the sort of friendly home computers that we all have today and probably are all sitting in our bags. And there was some sort of transition there, but ultimately what we're doing here, it's the same as getting getting a washing machine to wash your clothes, or I don't know, a human, like a self-driving car to drive you around. It is just doing something by hand, which you otherwise, but by automatically, which you might otherwise do by hand. And these are somehow quite important in the realm of chaos. I would just comment that yes, so perhaps back in the day, in the 1800s, if you wanted to study mathematics, you didn't have a well, I mean, somehow you didn't have a computer, so you were kind of limited in how much computation you could reasonably do, and so this sort of meant that stuff that where you didn't have to do too much to get something interesting was favored, and this tends to be things with nice symbolic structure, so you can like equations you can integrate or something like this. But of course, with chaos, we can't do this because there's no, I mean, often they don't have any kind of integrability or algebraic structure going on. We just have to, perform long time integrations to see what they do. And yeah, so this is a lot of work. And at some level, the modern study of chaos was really, as we know it at all, was really only enabled by computers. And in fact, it came out of a computation, at least, it is often said to have come out of a computational simulation. Edward Lorenz, he was a meteorologist, who was trying to, at some level, make meteorology something that had a sort of, let's say a quantitative foundation. So before it was kind of looking at stuff, and it was a bit of an art. Like you looked at your your past history of the weather, and you looked at your current observations. You were like, what does this look like? But he was really trying to make it physical. And so he wrote down some equations to study it, and obviously these equations were not integrable, so he had to do it on a computer, which was just becoming the fashion at the time, in the 60s. And so on a mechanical computer, a digital computer, and so he sort of ran some ODE, which had, I mean, 12 equations or whatever, and he said, okay, well, I mean, he ran it for a very long time. So one of these is this is actually from his original printouts. So it would have actually, the computer would have printed out the, no, it wouldn't have. So somehow the computer printed out a bunch of numbers, and then they plotted the numbers. And so he, originally the computer represented it to 6 digits, but it printed it out to 3 digits. So you have something like this. So, I mean, somehow, this is what they used to plot it, these 3 digits, because they figured, well, I mean, how much accuracy do you really need? But then he was like, well, I'd like to run it again once, like sometime. And so he did. And so this was the other curve here. As you can see, they approximate each other quite well, but as chaotic systems do, they ended up doing some really quite different things. They became completely out of alignment. And he really didn't understand this. I mean, this is a bit like one of, a mathematically important bug at some level, or at least he thought it was a bug. But it turned out that what actually it is just the exponential, the divergence of orbits, because the computer somehow didn't tell him exactly where it thought the system was. It gave it, some rounded off approximation, and the rounded off approximation was actually not good enough in forecasting what happened. So hence the sort of, the basic idea of chaos is something with sensitive dependence on initial conditions. I should say, yes. Why did I say non-hyperbolic chaos? I mean, hyperbolic chaos is also included in this talk. It will work fine. For those of you who are in the know or not in the know, basically this says something about how nice the geometrical structure of your chaos is, what directions you have expansion versus what directions you have contraction. If it's hyperbolic, then you have specific, quite sort of strong conditions on this. If it's non-hyperbolic, then you don't, and this is perhaps a lot more normal. So I mean, somehow this is, if you want to think about what's this, like if you just take a random dynamical, like a dynamical system at random, and you look at the behavior of it, I mean, often you get limit cycles, you get irrational rotations, but something like a circle map, X maps to X plus theta mod 1. But if you look at chaotic systems, almost all of them you will see in the real world, if you look at flow or anything like this, is going to be non-uniformly hyperbolic. And uniformly hyperbolic is really quite special, although you do see it quite a bit in pure maths. So yes. So yes, the rest of this talk is going to somehow try and talk about all the problems you have with non-hyperbolic systems and what you can do with it. Or at least that will be a part of it. Some of it will just be explaining some basic facts about it. So if we want to think about, okay, so I mean, generally the idea of dynamics is the long-term behavior of the orbit of some dynamical system. That's really what that's what we're, as dynamicists, what we're interested in. And okay, so what a really simple way to sort of understand this is just to, at least on a computer, is to just try and run a trajectory for a, so just start with some, okay, here's our dynamical system. So in fact, it's got a parameter here, A. So you can just imagine that this A is fixed. And okay, so it's just x times 1 minus x, and I probably should have plotted it, but we will see it in a moment. And okay, so the way that you run this is, so yeah, it's just a map on the interval on 0, 1. And well, somehow we want to run a long time series of it. So I'm just going to, define a function here that will do it for me. So with our parameter over a long time. And obviously well, okay, it sort of matters what our initial condition is. So we're going to say, well, we'll allow ourselves to specify this initial condition. And then, well, okay, we start with our initial condition. Well, we want to save it for a bit, right? But we start with our initial condition and we iterate it for a long time. So we say, okay, we're just going to apply the value of x at time n, apply the map to it, and we're going to get out the time in the future. And then somehow we get some long vector. So this is it's not very, that's not particularly obvious, but this is a vector that of length n, which is the length of our simulation. And well, we're going to fill it up. And so if we just start with 0 and we try and apply it to the logistic map, actually what we get is a let's say let's do it for something a bit shorter. There we go. So somehow we get something that is very how do you say, we get some absolutely trivial dynamics, but that's just because x is not a normal point of it. Sorry, I'll just go back. So if we make x something a bit different, I don't know, it's a number. We get a lot of, well, okay, we get a lot of numbers here, and it's, I suppose it's hard to see here because I've just printed out some numbers, but you can sort of see that this is not converging to anything in particular, going from x0 to x1, x2, x3, and so on. It's just kind of bouncing around. And in fact, if we do this, let's see if this works. Yes, here we go. Okay, so if we do this, we see that we get some rather irregular behavior. If I try and go to actually 3.8, which I think is here, no. But anyway, as you see, what was that? Yes, okay, so this is the system that we were simulating. You can see that there's a lot of sort of bouncing around here. The thing about the logistic map is a sort of really simple example of chaos, and I would love to draw it, but it is okay. So it's so this is time, and this is the iterates of the map. So the dots here are, okay, so it's discrete time. So actually I shouldn't really, how do you say, there shouldn't really be lines between this. It should just be a bunch of dots. Yeah. So yes, the lines connecting them don't really mean anything. It's just the dots because this is happening in discrete time. But you can see that it is somehow it's bouncing around everywhere, and it looks kind of messy. The thing about, well, okay, I suppose the thing about the logistic map, which is quite famous, is that if you that it actually contains for different values of this parameter a, it actually contains both chaotic systems. It has chaotic systems and has sort of systems that converge to some periodic orbit. So here you can see there's a periodic orbit of order 4. I mean, it's all a bit compressed here, but it goes like bop, 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 bop. If you want to think of it as like sound. But as you have already seen, there's a whole sort of array of things. And so, I mean, it's kind of famous here that you have some kind of period doubling, bifurcation to chaos, and then you get other sorts of things. So somehow a lot of systems that you actually have, a lot of systems are quite complex in terms of their behavior when you change this parameter. So, well, I mean, we could ask ourselves, you know, how can we actually tell whether we have a chaotic system or not a chaotic system? In particular, if we just look at some plot of the orbits like this, what distinguishes something like this from something more like this? Perhaps this is, well, this is something we'll kind of talk about in future, but maybe if you want to think about it, you could. Another question we could ask is, okay, here's a chaotic system. What distinguishes it from something, a sort of irrational rotation? So some dynamics that look like this, which is obviously something you can solve quite easily. The f to the n of x is just x plus 3.5 times n mod 2 pi. But I mean, this also looks kind of messy, right? So, and aperiodic. So just something to chew over, yes? Yes. For this one, yes. Sorry, as in for for this guy. No, hang on. Sorry, I'm confused. Yes. Yeah, totally. Square root 2. Oh, well, we can't do this. Can we do 1 on square root 2? Is that acceptable? What just happened there? Right. Okay, don't mind that. I think this is a little bug. Okay, so here you go. So you get something that's kind of a mess. No, but it's not. It's got regions where it looks periodic, but then it goes off and does something non-periodic. Yes. But this is yes. Okay. I mean, perhaps we'll see a bit later that there are some kinds of questions here about whether you can actually say whether a logistic map is chaotic or non-chaotic. And so somehow this, yeah, but we'll get there. So, okay, so I'm going to say, well, what can we actually see from these trajectories? And okay, so just as a note, I'm always going to talk about discrete time systems. You could have a continuous time system, so like an ODE, a differential equation. It's most of this is simpler, but perhaps there's some more technical things in some parts. So I'm just going to talk about discrete time. It's also a bit more natural for computers because you have to, somehow everything has to be discretized. And so if we just assume time is already discretized, we have less to worry about. Okay, so if we do look at at these trajectories, and let's say that we're not looking at a special trajectory like this 0, 0 that we had before, then somehow, okay, we want something that will tell us what's going to happen. And of course, because it's chaotic and it sort of bounces around everywhere and does all sorts of, is not easy to predict, and you generally can't write closed form solutions down. We need something that is going to capture it. And it turns out that the sort of natural, or perhaps a very nice, powerful thing we can do is use ideas in ergodic theory and study invariant measures of these systems. And in particular, we can study, well, the sort of perhaps nicest, the most important measure that you can study for, well, let's say many dynamical systems with some ergodicity, but particularly chaotic systems, is the so-called physical measure. So this is somehow let's say it's the measure that if you take a Lebesgue generic initial condition. So this is somehow, if you randomly sample your phase space M, your phase space M, you just take a random point. Then with positive probability, if you take a long time series of this, so we look at f to the n well, like the iterates of this initial condition, that time series is going to sort of pile up and start looking like this physical measure if you take some kind of, say, histogram of it. Now, I mean, measures are kind of sort of slightly unpleasant things. We don't want to impose too much structure on them. So really when we talk about sort of studying measures, we're actually going to talk about studying averages with respect to the measure. So here we're going to do what is called the Birkhoff sum. And we're going to take some function A, say some continuous function A from the phase space of the function of the phase space of the map of the dynamical system into the real, well, let's say into the real numbers. And we're going to sum it up. But then we're going to take an average over a long time. And the idea of a physical measure is that if you do this, then you should expect to recover an average with respect to the physical measure for any nice enough function A. And for, let's say, for Lebesgue, almost all, or for at least a positive measure set of parameters E, parameters, initial conditions X. So why Lebesgue measure? Because, I mean, somehow this is the most, this is the thing you see in real life. If you sort of, it looks like, say, like a normal distribution, which is sort of kind of random error you see everywhere. Or, it's absolutely continuous with respect to. I hope we can all agree that the Lebesgue measure is a very natural thing to look at. So, okay.
They always find this fact that this average compared to numerical physical method quite amazing.
Yeah, I mean, I will talk about that a bit later. I mean, I think perhaps, yeah, there's some magic to that, which might go a bit beyond the usual reasons that people talk about, but yeah, there's some, I'll talk about it later. Okay, so yeah, so if we actually want to look at what these Birkhoff averages look like, we have this, how would you say this, sorry, okay, so I mean, this is what taking a Birkhoff average looks like in code. So I mean, I should say what code I'm using. This is Julia. It looks a bit like Python. It looks a bit like MATLAB. It's nice. It's fun. Okay, so but I suppose somehow, and I suppose in this numerics course we should have some numerics. So okay, so somehow the idea of this is that we have okay, so here's our observable. It's just x squared. So this is a map from the phase space of this logistic map, which is 0, 1, into the reals. We're just going to try this a few times, but what we're going to do, the idea of taking a Birkhoff sum looks a bit like this. So, well, okay, so this is just the same thing we did before. We just kind of took some time series of our system. We iterated it a bunch. We reiterated our map a bunch, and we got out some vector xh of the history. And then we say, okay, well, okay, this is perhaps a little bit obvious. So we take, let's say, I wish I had thought about this bit and wrote it a bit more transparently. Yeah, this is not very transparent at all. But I mean, basically, what this function here does is it gives you the Birkhoff for every n, every element is going to give you the Birkhoff sum of come on. It's going to give you the Birkhoff. It's going to give you this. This thing inside here. So, and if we plot that, we can see that as we run our simulation for a long time, for each different sort of initialization here. So in this case, for every time I've initialized my. All right, let's make it a bit shorter. Make this a bit shorter as well, so it's easy to see. Okay, so you can see I've run my time series a few times, and each time we have, each of these corresponds to a different time series. I've taken my average, and you can see that it converges. There seems to be some limit here to which it converges. And you can ask, well, how fast does it converge? How do I choose it? I choose it randomly. So this rand command, which is pretty standard in a lot of languages. Yeah. But I mean, just for everyone. So this rand command basically samples a number uniformly on 0, 1. So somehow this is like Lebesgue measure on 0, 1, right? The computer version of it. Of course, there's a few caveats to that, but let's not think too deeply about it right now. Yes. So this is the idea of Birkhoff mean. And actually, you can have a more physical definition of this. This is a bit irritating, isn't it? I wonder why it's doing that. Okay. Okay, sorry. Yes. So in this, so what we're going to do here is we're going to plot a bunch of, we look at our Birkhoff averages over a long time, but for let's say a sort of, a bump function on some set E. So this function here is 1 if this is in E, and it's 0 if this is not in E. What this sum here is actually doing is it's telling you, well, this is telling you the number of points in the forward orbit of X that are in this bin, that are inside E, because you I suppose, each time this is in E, this adds 1. And then it's dividing it by the total number of points. So it's saying it's the proportion of points in this orbit for time n that lies in this bin. And well, if you do that, what you get is something like, okay, so we can actually see it. What you get is something like this. So, okay, I should explain to you what this is. So each line here is the average, is the Birkhoff average of a how would you say, is the Birkhoff average of the sort of, like this characteristic function that I just put up there, for where the set of the characteristic function is, I suppose, the sort of part of this interval that contains, that the bar contains. Yeah, oh, that's also irritating, isn't it? I'm sorry. I'm just going to take this moment to complain about the software I'm using here. Okay, so so this is the Jupyter Notebook, which is this thing where you can type in code and it will spit out an answer for you. It's a sort of slideshow version of that, but the nice thing is that it means you can type in code. Jupyter Notebooks in general are very good, so they run with a lot of, they run with a lot of computer things. Well, not MATLAB, because MATLAB has its own thing, but sort of R and Julia and Python and perhaps even maybe C. No, probably not C because it's not interpreted. Anyway, they're really nice. They're great. It's a shame about this presentation software. So you right. Yes. So if we take so perhaps it's been easier to see like this. Why does it do that? There we go. Right. So okay. So you take this set and so say from 0.1 to 0.2, and you run this Birkhoff average over it, and you get out something that looks, so then the proportion of time that it spends in this bin is 0.05, apparently, for our time simulation, and you get something that looks like this. But anyway, the n, no, it shouldn't necessarily, because it should actually converge to the average of the integral of this function here with respect to the physical measure. That's what it should look like. Which is just row of E, like the measure of this set E with respect to the physical measure. And so if we do this, so if we actually do this, and again over, we make our sets E small enough, we can sort of get some idea of. Okay, we get some idea of the sort of distribution of our measure, and as you can see here, it actually looks it looks a bit. I mean, it's obviously got all these spikes and so on, but it actually looks kind of nice in the sense that it is absolutely continuous. It appears to have some kind of density function, and this is sort of yes. See periodic islands. What do you mean by periodic islands? It is mixing. Yeah. Yes. I think it is a theorem. Well, no, it is not a theorem. This is something that we're going to get into. But I mean, it's how would you say? It appears to be a theorem. No, it doesn't appear to be a theorem. Like, it appears to be true. It very much appears to be true. And there's no like tiny. Well, I mean, maybe there's a tiny stable periodic orbit, but we don't know. Yes, nearby, yes. Are you saying, hang on, Alexi, are you saying is it chaotic up to being mixed? Like assuming it's chaotic, is it mixing? Like, does it not have any periodic blocks? Oh yeah. No, it's actually exponentially mixing. It's actually exponentially mixing. Yeah. Yes. So no, there's no cycles. Okay. And okay, so actually maybe somewhere we can see one of these examples. Yeah, here you go. So here's something where there's two blocks. Yeah. Okay, so again, like if we look at different kinds of different parameters of the logistic map, you can see that you get these kinds of distributions, in particular, okay, so somehow you do see different kinds of physical measures for chaotic systems. So here you get some kind of distribution across the phase space, but then if you have a regular parameter, you will see. So when I mean regular, I mean converging to periodic orbit. You will see that the physical measure is actually just the somehow the uniform measure over this periodic orbit. Because if you run your periodic orbit over the long time, it's just going like bup, 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 bup. Well, actually, if you imagine that those are all the same notes, I don't know. Say it's just cycling like this, then somehow this over time, this is the sort of integral you get. So you can see, yeah, I mean, you see qualitative differences for these guys. All right. So then perhaps, how are we going for time? Maybe I will just get a phone so I don't have to keep those. Okay. That's not. Sorry. There's perfect. That's the clock is wrong. Yeah. Well, okay. The clock is 2 hours and 10 minutes wrong. So everyone remember this. Yes. Good. How are we going for slides? Okay. So we can then ask us, okay. Maybe we want to just take a minute's pause to rest our brains. So think about something. Okay, yes, but then we need everyone needs to write down put the password in if yes, but you need to log in. So maybe if you don't have Eduroam, you should take your computer out right now and put it in, because I remember I've done this at conferences where I've forgotten that there's
I think you can turn it, and if we need it again, then you can.
Yes, all right. Well, don't do that then. Okay, I'm actually okay. So maybe now that we've had we've rested our brains a bit, very briefly. Let's think about, okay, so then I suppose we can ask, well, how do we actually know we have chaotic dynamics? And one of these is that we can look at it, but we don't necessarily, I mean, again, I showed you that quasi-periodic picture there. So it's not immediately obvious just by looking at something, whether it's chaotic. Fortunately, there are various ways to check. And one of these, I guess, the most sort of, let's say, obvious, the most direct from the definition of chaos is to look at the Lyapunov exponent. So, well, the top Lyapunov exponent, which is this idea here, it's sort of looking at the growth of the Jacobian of the map. So obviously to use this, we need to know the Jacobian of the map, but let's say, so of course, what this does is it somehow, it measures, if you take two orbits that are points that are very close together, like that, those two initial conditions that Lorentz had to think about, and you look at the distance between them, well, somehow, as long as y and x are very, very close, the distance looks something like, you can linearize it and look at, say that this distance is something like, is given by this operator here. And if we range this over all possible y's we could take, then somehow the distance looks like this derivative here. And the thing about chaos is, as we probably all know, this explodes, it grows exponentially with n. And so this Lyapunov exponent here is positive for chaos. Well, sort of, if everything goes well. Right. Of course, if we have convergence to a fixed point, say, so there's some sink, there's some stable fixed point, let's say, then this Jacobian here generally, because somehow f is going to be a contraction, at least locally, and this Jacobian is going to be less than 0. Okay, so somehow if we can compute this Lyapunov exponent, then it tells you for a generic, let's say for a generic x naught, then it will tell you what the behavior of your it will tell you about the dynamics of your system. But of course, this is a limit. Oh yes, and we can relate this to Birkhoff averages, because in one dimension, this Jacobian here is really just a derivative. Well, the norm of the Jacobian is just the norm of the derivative, and so it looks like a Birkhoff sum with observable log of the absolute value of f dash. So when I had some little things on the graphs with the time series saying whether something was chaotic or not. And so, well, if you do this, if you want to do this somehow for the logistic map, you just need you need your parameter. Well, you can do this, and it's the same idea as a Birkhoff sum. Like okay, so this is taking a Birkhoff sum. You start with sum 0, and you iterate your dynamics a lot, and then you add the thing that you're trying to approximate, and okay, then you divide by n because you want a mean. And you get up something like this. And so then I was saying, well, if this is positive, I say it's chaotic. And then if it's negative, I say it's periodic. And but of course, we're assuming that taking, like in a computer, again, everything has to be finite. We are assuming that if we take a finite, we just take this for fixed n as opposed to taking the limit, that we're going to get the right answer. And this is not, well, we will see that this is not always correct, and perhaps this comes out of this is related to a sort of kind of, let's say, a fundamental result about the chaos for the logistic map, which you should think of as in some ways being like a model for more complex sort of chaotic systems that aren't hyperbolic. There will be some differences because it's perhaps the one that we know the most about, so we pretend it's like everything. or we not pretend, but yeah, we can say, well, maybe we can draw some insights. We have this, anyway, for the logistic map, we have this kind of, let's say, trichotomy. So for these parameters A, which go from 0 to 4, we can write it as a disjoint union of one parameter set, which is the set of chaotic parameters. And okay, this is somehow a positive Lebesgue measure in 0, 4, so we're likely to see it. But it is also nowhere dense. So I'll show you what that looks like. There's a sort of nasty set, which is neither periodic nor chaotic, which is 0 Lebesgue measure. So that is to say that if you randomly chose a point in 0, 4, uniformly you use your rand function, well, whatever, you use the sort of, infinite precision rand function, then you would get, you would somehow never see this unless you got sort of world-endingly unlucky, like, it is, don't worry about it. I think it is open. Okay. There is an open dense set AP, which contains all the periodic orbits. It is also dense, and it has positive Lebesgue measures. So what that looks like, here is a, let's say, a plot of all the different measures of the logistic map, going from, I think, about 3.5 to 4. So as you could, so the measures here that look like this, that are sort of made up of, say, a few lines, are the periodic parameters. So you have somehow, if you think about a slice here as like a histogram, that kind of histogram, you can see that you have this 3-point guy. Also, you have a finite number of points. But then the ones here that look kind of gray are where the measure is distributed across a large set of values. So this is so this here is parameters A, and this here is the phase space going from 0 to 1. And you can see that there's, okay, so somehow you can see that there's a lot of gray point, there's a lot of periodic points and a lot of chaotic points. As the theorem says, there's a sort of positive measure set of all of them. But you can see that these periodic orbits, well, I mean, these, like the sets of periodic parameters, you can see that they kind of, I mean, they exist in bands, right? And everything inside this band, or inside this band, is periodic. But then there's bands, I mean, perhaps it's becomes harder and harder to see at smaller resolutions, but you can see that these bands are kind of everywhere. And in fact, they are, well, the bands become smaller and smaller, but they exist everywhere inside these, inside this set. There's every point in this set is arbitrarily close to a band. And even though the sort of set of chaotic parameters, which is where you don't have the bands, is a positive measure. I mean, it's one of these awful sort of unintuitive things about measure theory that you can do this. Well, I mean, this actually gives us computational problems, because if we want to look at a chaotic parameter, then, well, because chaotic computational systems are kind of finite, we're never going to actually exactly zero in on a chaotic parameter, or at least, somehow there's going to be some kind of uncertainty. If we like say that we want to approximate the chaotic parameter for pi on 4, right? The logistic map for parameter pi on 4, so that may be chaotic or may not, but like we're never going to be able to actually get pi on 4. We're going to get something that's close to pi on 4, and that could just be regular, which is completely, and then maybe look completely different to the actual, the actual chaotic parameter. And so somehow this is called structural instability, or it's sort of an example of structural instability. And well, we could ask why it is. It basically, like, where this comes from. So at some level, there's nothing necessarily in the logistic. I mean, in sort of, in a simplified sense, there's not necessarily any reason to not have any stable periodic orbits in your logistic map. And indeed, I mean, here we can, if we just go back a bit, can I go back a bit? I'd like to go back a bit. If we look at this guy, we like, there doesn't really appear to be any, let's say, like, nice, obvious pattern as to what, I mean, there are in some senses, but there's not any particular pattern as to where exactly these periodic orbits fall. Perhaps the order they fall in, but that's different. So somehow that you get chaos when you don't get these stable periodic orbits, and of course it does happen then, but there's no and of course, okay, so somehow you can use this to try and estimate the measure of this system, and maybe this is something to go away and do if you feel like doing some exercises to try and figure out the Lebesgue measure of the set of parameters with chaotic values, perhaps just by simulating. But yeah, what was the point? Yeah, you basically you just have to show that something doesn't happen, which is to have a sink. That's kind of the a way of thinking about how the chaos, how you get chaos. It's not exactly true, but it's close to being true. So, but the thing is that if you have a chaotic orbit, and let's say then it's very easy to get a sink. So say if you take 0.5, which is the critical point of the logistic map, and I will actually just draw a picture of it. Oh, so I hope you, hello. Hope you got that picture. So the logistic map looks like. Looks like this. This is 0.5. So you can see here that the derivative of f of x is 0 here. So if you try and say take the derivative of 0.5, then well, the forward derivative, then it's always going to be 0, no matter how many iterates you take. So if 0.5 ever comes back to itself, goes to here, goes to, I don't know, here or whatever, goes to here, then if 0.5 is periodic, then this is always going to be a stable periodic orbit. And so we can't have a chaotic system. You can't have chaos. At least, I mean, this is, yeah, in one dimension. Anyway, we're not going to have chaos. So in this case, I'm just going to check which one is which here. Okay, so ignore this. So if we look at this, right? So here we take our 3.8. Start at 3.8, which is that parameter I was looking at, and we can see that it's chaotic. You can see here's the forward orbit of 0.5 is given with this orange line, and well, actually it keeps going on forever, and you can see it kind of bounces around. But if we just move our parameter a bit, we can move the orbit of 0.5 closer and closer to 0.5 itself until, let's say, it's basically on top of it. And then we get some kind of regular. We have a sink here, and so the dynamics, as done by my little test up here, show that we get some regular behavior. But the thing is that we can also do this for, so this was kind of looking at trying to get a period, order 4 period of the logistic map, but we could also try and get sort of a longer orbit here. And then you will see that the amount, because our orbit is very sensitive to the initial conditions, we really only need to change our parameter at a much smaller amount to get, there we go, to get our orbit to fall on top of itself again. So you can keep doing this for longer and longer sort of periods of the map and get regular parameters at closer and closer values to the original 3.8. So that's kind of what that's doing. How are we going to say yes? I mean, so that more or less that's sort of what happens. And I mean, again, if you want to do sort of harder numerical exercise, you could try and find by sort of, I mean, say starting by 3.8 and then moving your parameter around a bit to try and make a periodic orbit of 0.5, you can try and find a logistic parameter with a stable orbit of some given length. That's perhaps a cute little thing to do. Anyway, but what this, I mean, somehow this explains why we have this kind of instability here. But then you've got to ask yourself, well, at least if we don't know something quite special about the logistic map, how do you actually tell if we have, if our system is chaotic? Because we could just run our system for a very long time and, you know, we could fall into one of these sort of period, like these very long, like perhaps an arbitrarily long periodic orbit. And I mean, that's going to take an arbitrarily long time to see that we've done that. Okay, so somehow there are sort of theoretical solutions to this, but I mean, it really does always come down to knowing the behavior of some orbit for all time. Yeah, I mean, this is a difficult question that I think, well, somehow this is the problem for computation, and there are various people here who've thought about it. And I will give you a little illustration of this. So if we run, I've taken a particular parameter here. Let's just doing this again. Great. Okay, so I've taken you know, a time series of length 100, let's say 1,000, and I've run it, and at the end of this time series, we can see that we've got some kind of well, some kind of chaotic behavior, and this is what the histogram of our time series looks like. So we've done I mean, this is not, so there's a lot of stuff here that's not in the code that's not particularly readable, but I mean, we've done a histogram. But the thing is that if we keep running it, okay, we still get chaos, and so we think, well, maybe we have chaos, but if we do this for long enough, we find that actually in the end we have periodic behavior. So what's happened is our system has run. If we've run our system for a very long time, and we found that okay. And so over short times, you know, we've seen some kind of chaos, but then in a long time, eventually we've ended up in a let's say in a hole, in some stable periodic orbit. It looks like this, and it's all. I mean, you can. I don't know how easy it is to see. I mean, you can see there's the This is it's very long. I think it's of order 34, so it takes 34 times to go around. But I mean, yeah. Of your computation. Well, you could do it by. Well, it's so okay. Okay, so yeah, so you're saying, how do you know that you haven't it's not just the fact that you've got, you know, a finite precision for your thing, and you've run it through a finite state. Somehow there's a finite number of numbers that your computer can encode, and you've run it through a finite, like it's gone through its state space, and it's just found some periodic orbit. The answer, well, you know, I suppose the answer to that is that if you do have this and it genuinely is chaotic, if you start at a different fixed point, if you start with a different initial condition, you should find a different periodic orbit. Somehow the state space tends to have multiple different sort of periodic orbits that coexist like that. But in this case, we still see the same periodic orbit. So yeah, it is.
So we know that in this case for the logistic map, this doesn't happen, but it could be the case that we have an attractor which is chaotic, which has 34 intervals which make the attractor. And so if you have only use finite number in your approximations of the points, you only see this final number of bits.
Yes. Oh, so you have like an attractor with, you know, with width, I mean, smaller than the precision of
exactly.
Yes. So, well, in fact, in this case, what you would do is you would compute the Lyapunov exponent of this orbit, and you would see that, because the Lyapunov exponent is stable to small, like the derivative is stable to small perturbations. So if you did have some on your interval, you had a bunch of some very small chaotic orbits. Let's say this is 3, and it went like this. So your point went somewhere in here, went somewhere in here, went somewhere in here. And you take well, somehow, like if you, the derivative inside here should, and here should all be quite similar. And unless, I mean, I suppose the way that would work is that it's on top of, for this to work, maybe you need it to be on top of the, to get your topological complexity, you need it to be on top of the, oh, does this need to be in the, yeah, okay. Sorry to everyone on Zoom. Okay. So, so somehow to have on an interval to have a chaotic system, it can't be one to, like, you can't be one to one. You need to have some multiple points mapping under F to the same point. So if you just had 3 intervals here, here, and I don't know, here or something, that's not going to work because you it's not chaotic. You need to have some chaos. So what happens is that your periodic orbit, your little interval has to sit on here. So you have some folding as well as some stretching. And so if that were to happen, something here would have to sit, it'd have to sit on 0.5. And I can tell you that while it does sit very close to 0.5, it does not actually sit on, it sits at, you know, a reasonable distance, enough of a distance away from it to know that it's sort of not, it's not really chaos. It's not hiding some chaos there. Yeah, so I mean, somehow you may need to worry about these kinds of fine things, but if you do have a periodic orbit, you can actually compute that there is a periodic orbit in general. It is possible to rule that one out, you know, with a finite amount of effort. Yes, and in that case, it's negative. Yeah. Yes. So yeah, but I mean, in terms of actually, sorry. Okay. Yeah. But I mean, so somehow, if we're doing this long simulation, how long we can ask ourselves, well, how long does it actually take to find this? Actually, to find this. This periodic orbit, how long does it actually take to, come on, how long does it actually take to, we'll get there. Okay, so here, you know, here's this chaos. How long to actually take to get to this point? So here, even though we have a periodic orbit, here we can't see that we have a periodic orbit because we're not, I mean, somehow we're just kind of bouncing everywhere, whereas here we can actually see that we're doing something in a periodic kind of fashion. And so, okay, so I've done some kind of iterative numerics to do this, and I won't go into it, but you can actually plot, let's say, the sort of region of phase space where you actually have some kind of, let's say, linear convergence to your periodic orbit. So it's not like you're bouncing around and eventually you find the periodic orbit. It's like you're actually, I mean, it's where you found the periodic orbit. And the sort of measure of phase space for which that is the case for this periodic orbit of length 34 is of order 10 to the minus 5. So you had to, so I mean, this is why we had to iterate for 1 million time steps to actually see it, because it's the sort of width of this periodic orbit is very small. So I mean, this is somehow the challenge. There may be some periodic orbit, some sort of stable long-term behavior of your system that you will take such an incredibly long time to see, because it's just, you know, it's like you know, you're kind of, it's like finding a needle in a haystack. You're just kind of, you know, searching blindly, chaotically, and eventually you kind of happen upon this needle. But if the haystack's big enough, it's going to take a very long time. Dynamical space. Yes. Well, I mean, the whole thing is the basin of the attraction of the periodic orbit, but like it's the basin of the attraction where the dynamics is, you know, conjugate to the periodic orbit. It's like, say everything in 0, 1 is actually converging to the periodic orbit, but if you have I mean, if this is your orbit, it's a set of points for where you map from, let's say, this interval, like an interval around the periodic orbit, into an interval around the periodic orbit, into another interval around the periodic orbit, and then back, as opposed to, you know, bouncing around and then eventually finding it. Yes. So it's stuff that if you looked at a graph, you'd be like, that's periodic. So yes, and of course, I mean, you know, yes. Okay. So in practical terms, I mean, you know, if you're only interested, I don't know, if you're only interested in the behavior of your system for, you know, 1,000 years or something, then you sort of don't really care about these things. You can sort of imagine like they don't exist, and there's sort of various mathematical ways to think about that as sort of a sort of map with a hole, for example, a conditional, absolutely continuous, a conditional physical invariant measure, okay, but somehow, perhaps if you're really, you know, in a sort of real dynamical sense, you know, sort of, you know, what happens at infinity, that could be a problem. And okay, but there is some good news here, which is that if you do have a period, if you just randomly choose a you know, a parameter, and that parameter turns out to be chaotic, then it's much more likely that this parameter is going to be of some kind of low order. So instead of being of order 34, it's of order 3, let's say. So what this plot here is saying is that this is the sort of measure in parameter space. So this is the amount of these A's for which you get a periodic orbit of order whatever this is. So so you can see that there's some kind of, let's say, there's some scaling behavior here. So it's saying that if you have a very long periodic orbit, which you might sort of let's say to skip over a few things, you might expect to have be small in parameter space. So for example, for this other one, for this one that we saw here, the reason that I wrote, where are we? Here, the reason that I wrote this many digits here is because this is actually, like, this is the number of digits you actually need to see this periodic orbit. If I made that a 3, the last digit a 3 or a 5, you wouldn't see it. So somehow you're very unlikely to actually find this particular orbit. But I mean, there's a lot of them. But what this tells you is that somehow you're actually really quite unlikely to find some orbit of length, you know, well, of length 34, but of length something very long. Also, notwithstanding this is not a complete survey of all of them, but it's a survey of all the biggish ones. So somehow what this is telling you is that you don't, even though you can fall into these, you know, find these needles in haystacks, there aren't actually all that many needles sitting around. And so if you search for a long enough time, you can, you know, you can't be 100% sure, but you can be some percentage sure that you have found, some large percentage sure that you have found something that is actually chaotic. And well, somehow, because we have to, you know, like to actually nail it down 100%, we need to think about something at infinity. This is sort of when you look at a lot of, say, like non-structurally stable chaotic systems, this is kind of how you have to think. You have to be like, yes, I am, you know, I am pretty sure that this is what I think it is. Yes. So how are we going for time? Okay. Should I leave some time? I suppose I should leave. Okay. Yeah. Okay. Okay. Cool. Okay. So I suppose just perhaps two things to finish with. The first one is that, as I've sort of been kind of saying at the edge here, when we use a computer and when we do specifically a kind of approximative kinds of things. So we're not using Mathematica to compute something symbolically. We're just, you know, getting on a computer, and I mean, somehow we're trying to approximate some number by using by adding a lot of things together, or whatever it is we're doing. We're doing this in floating point arithmetic. So this is somehow finite, and it well, I suppose the idea of it is that you have some you approximate, say, like pi by well, up to a certain number of significant digits, and this significant, I mean, the digits happen in binary, but we can just say, well, okay, somehow, you know, you take 53 binary digits after the first one, in this case, which approximates to about 16 digits in base 10, and you just, you know, when you do an operation, you know, if you can't, if I say pi times pi, I mean, so hang on, pi is, let's say, okay, so if pi is this number, well, I mean, so we're approximating pi by something like this. That is what it actually, Julia actually sees when it does computations, mostly. Well, okay, if we multiply two of these together, we'd expect, because the original one had, you know, 16 digits here, we'd expect that if we multiplied them, we'd get something with 32 digits at the end. I mean, you've all had to multiply, you know, fractions of decimals in primary school. You would probably remember this. But in fact, what it has to do, because it can only represent a certain number of digits, it has to truncate at some point. And this, well, okay, so somehow this is always going to introduce errors. We can sort of mitigate these errors by you know, using higher precision things. So this big float here, well, you can change the number of digits, will do as many digits as you want it to do. So I think in this case, it's going to do 256 binary digits, so 80 something, I think, maybe. Anyway, so somehow this you can always improve your calculation, but it's always going to be slower when you do that. There will be some error, but anyway, there will be some errors. And in fact, here, if you do this in your head or whatever, you can see that this should be, the answer should be 500, but in fact, it's not 500. So sometimes you actually get, you know, you do get obviously the wrong thing. Well, okay, so in chaos, this is kind of a pretty serious worry. Because somehow we have this, we know that, I mean, and this comes back to the original Lorentz thing. We know that if we do make some tiny error, this tiny error is going to get massively magnified. Well, how can we sample our physical measure? Because, you know, we don't know, I mean, unless we start with, you know, 1 billion digits and we, you know, however, whatever. It turns out this is kind of not really a problem. And there's a few justifications for this. One of them is shadowing, which is something to look up, but I won't talk about it. But basically, the way people like to think of this is that if everything is good, the kind of error you get from your floating point approximation, so from truncating those digits, behaves kind of randomly. And a nice property of physical measures is that, which I haven't mentioned so far, but it is often true, is that if you introduce some sort of noise to your system, so instead of taking the logistic map, I then add some kind of noise, maybe not, maybe times the uniform, 0, epsilon, for some very small epsilon. As we take the size of our noise to 0, it's going to, we will sort of recover the non-stochastic discrete measure. Yeah, so somehow, this is a nice, so when you have, you know, in a stochastic system with a nice noise, you only get one invariant, well, you get a finite number of invariant measures, but one of which will be the physical measure. Well, I mean, so if it's ergodic, then it will be the physical, there will be one measure. And as you take the noise to 0, you should recover the physical measure, which is actually a problem for us because it makes it hard to sample other invariant measures. But yeah, this somehow is, I mean, it's obviously not airtight because it's not a random, it's not like this cutting off is not random. But, you know, for many systems, it should work fine. Although, again, you run into this finite state space issue, and there's sort of arguments that say that if you if the your floating point representation of your phase space which is usually of this size, is p, then you should sample it for about root p points, because after that you might get into some periodic orbit like Paolo was talking about. This is a sort of, let's say, looking at it from simulations, but this is something that do the what? You can change, but by default it's always the same, but you can change it. Randomize the cutoff. Well, you always can. It depends on how, but it might be slow to do that. One thing that you can actually, okay, so I will show you one thing that you can do that sort of makes it a bit more. Yes.
I mean, the periodic part of the behavior or the chaotic part. I mean, you may actually don't know if those changes are due to the stochastic behavior of the noise or the actual dynamics. So pragmatically speaking, it's very difficult to assess. So if you can comment on that, thank you.
Yes, absolutely. Yeah. So I mean, I'm not even sure to what extent the stochastically stable thing applies to the logistic map. So I mean, I suppose this convergence happens as the noise goes to zero. I mean, that's just that there's no quantitative bound on it. It's just saying that if you make it small enough, it'll work, but you don't know how small you need to make it in practice.
The noise.
The noise, yeah.
So it works if the noise tends to zero? Yeah,
but just in the limit.
Okay.
But I mean, somehow, it's this noise. I mean, you could make this noise, I mean, for the floating point discretization, this noise is like 10 to the minus 16. So that's really, really small. You'd hope that it would behave correctly. Yeah.
Thank you.
But some dynamical systems don't behave well. And one example of this is the doubling map, which is perhaps, let's say, another very simple chaotic map. So it's just you take a number, you multiply it by 2, and you cut off the non-fractional bit. So here we got 2042 blah 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 blah, goes to 408 blah 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 817, and then this will go to 1.63 blah blah, but it goes to 0.634. And you keep doing this, and if you do it on, I mean, and so this is chaotic, and I mean, it should just bounce around forever for a generic initial condition. Well, if you do it on a computer, you see that you like, no matter how you start it, we just try something different, you see that you always get, you always end up at 0. And I mean, the reason for this actually comes out of the binary expansion. This is going to be 53 ones and zeros in binary. And so if you multiply it by 2, well, that's just like shifting everything forward by 1. It's like if we multiply by 10, in fact, we could just do this. Let's not make it the doubling map. It's now the 10ing map. I don't know. If we do this, you can see, hey, not 10x. Why is it not doing that right? Is it doing that right? Yes, it is. Sorry, I'm just can't read this. Okay, so 84078 blah blah blah, 40798 blah 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 blah, 09798 blah 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 blah. So I mean, it's just moving the digits 1 over. And actually, because this and anyway, so and then you can see. I mean, so somehow it's not quite the same here, but at the end, I mean, there's something else going on here a little bit. But at the end, you can see that eventually you're just cutting all this, and you eventually run out of digits. This is what's happening in the binary version as well. Yeah, no, exactly, yeah. So this isn't quite right, but yeah, if you did it on a computer with 10 digits, you would definitely see this. So somehow you have to when you run your long iterations, you need to just think a little bit and make sure that your map is not going to behave like this. Like for pretty much anything other than the doubling map, it won't. But one way you can actually fix this is by adding a tiny amount of noise. So this noise eps here is the smallest precision. So it's like saying like this is like the smallest number that you could, like the difference between this number and the next number that it can represent. And okay, so if we just add something that's a few times that precision times a random variable, you can see that actually this issue of running out of digits disappears. And in fact, you will get something out here that if I were to give you a histogram, it would look exactly like the physical measure of the doubling map. But yeah, generally, if you're worried about the precision, you just add a bit of noise, and it will sort of carry you through. And it's such a small amount of noise that it won't make your results less valid in a meaningful sense. So I've got 5 minutes, so maybe I will talk about this next time. But somehow, if I were to conclude, we can do a lot with computers. They're great for calculating. They do have the problem that you have to make everything finite. The amount of time you use to iterate to see if it's chaotic, discretizing the numbers, your space, and therefore the numbers that you use, and this introduces errors. And okay, so somehow we have to think about, if we really, like, depending on how, well, to some extent, no matter how, sort of how pure and how applied we are, we need to just think a little bit about, is this error going to screw things up for us? And including in cases where we actually don't really know whether it will or it won't. And so, well, there's different levels of rigor, and you need to think, I think it's worth thinking a bit about these different levels of rigor and where we do apply this, different kinds in different places. And I should say that they are all useful, and we all use different ones at different times, but probably there's not really time to go into it. But yes, maybe I will talk about it next time. But we've seen some ideas about how we can sort of, let's say, try and quantify how much we don't know in various ways in this talk. And next talk, I will talk more about that, quantifying our errors. So, but it's good to end on time. So thank you.
Pleasure to introduce Philipp, who will talk about the dichotomy results for eventually always simplified statistics.
Yes, thank you very much for the introduction and the invitation to speak at this workshop. It's very nice to be in Pisa all the time. So yeah, my talk has kind of two aspects. So on the one hand, to study the recurrence behavior of typical orbits in a dynamical system. And the other aspect is to see to which extent results from probability theory for IID processes can be transferred, or to which extent one can find analogs in the setting of dynamical systems. So, and okay, and in dynamical system, this is related to so-called shrinking target problems, where we want to study the recurrence behavior of typical orbits. So the very general setting is that you look at a probability space and a measure preserving transformation acting on it. And then you consider a sequence of subsets whose measure goes to 0. And yeah, we refer to that as a sequence of shrinking targets. And typically one studies so-called nested sequences. So where we have this, that the m plus first set in our sequence is contained in the mth target set. So you can think of this picture here. So you have a sequence of shrinking targets, typically around a fixed center, denoted here by x0. And classical shrinking target problem in a dynamical system asks, okay, if you have such a shrinking sequence of targets, do you hit this sequence infinitely often? So you look at those initial point x in our probability space x, such that the orbit of that initial point x, that the nth point, the nth iterate of that point x lies in the nth target set, and that this happens infinitely many times. So in a set theoretic notation, you can write it like this. So you want to have infinitely many hits. So that's why you look here at, okay, the union over the pre-image of your nth target set here. And you want to hit it at time n. So that's why we look at the nth pre-image of this. And yeah, since you want to have infinitely many, it's you take here the intersection over m, and here you have the union over n starting at m. So this is a lim sup set of this form. And as a kind of first observation, so if we have such a nested sequence of targets, then this set of infinitely many hitting or the points that hit the target sequence infinitely many times, this is a T-invariant set. So, okay, this is one proof of this talk. Maybe hopefully we will get to another ones later, but let me start with this observation here. So we want to check that this set H infinitely often, that this is a T-invariant set. So if our point X lies in it, then by definition, that means that, for infinitely many n, we have that Tnx lies in the n's target set. So this nth iterate, we can write it in this way here. And now we use that our sequence of targets is nested. So the nth target set is contained in the n minus first target set. So we see that our point Tx also lies infinitely many times in the target sequence. Because so we see for our point Tx, now we have that n minus first iterate lies in the n minus first target set. So our point Tx also lies in H infinitely often. And yeah, hence we have that H infinitely often is contained in the pre-image of the set under the transformation T, and then we explore, then we get this, that its measure is at most the measure of this one, and now we use that our transformation T is measure preserving, and so we see that, the measure here is the same. So our set is invariant up to a set of measure 0. So that says that if our transformation T is ergodic, and we have such a nested sequence of shrinking targets, that then this set of points who hit this target sequence infinitely often is either a set of measure 0 or of full measure 1. So we have a 0-1 law for the measure of this infinitely often hitting points. And so you could ask, okay, under what conditions on the decay rate of your sequence of targets do we have that is hitting infinitely often, has measure 0 or has measure 1? And of course, from classical probability theory, if we remember that our set of infinitely often hitting points is a lim sup set, we kind of, in probability theory, we have the Borel-Cantelli lemma that says that, okay, if we have such a sequence of events and the sum of the measures of these sets is finite, that then the lim sup set has measure 0. So that part we can directly apply on our sequence here of the nth preimage of our set Bn that we have here in our lim sup set, the way how we wrote this set of infinitely often hitting points. And we see that if the sum of the measures of our target sets, if that one converges, then the set of infinitely often hitting points is a set of measure 0. So for the converse direction, the Borel-Cantelli lemma requires that these events are pairwise independent. So this is clearly not given in a dynamical setting because there we have this dependency. So the question is, okay, to which extent can we find an analog of such a this Borel-Cantelli lemma and from classical probability theory in the setting of dynamical systems? Yeah. And we say that such a transformation T satisfies a dynamical Borel-Cantelli lemma if for some family of nested targets Bm, we have kind of, yeah, this dynamical Borel-Cantelli version that, okay, we know already that if the sum of the measures converges, then this so the measure of the infinitely often hitting points is 0. And if we have this other direction, that if the sum of the measures of the targets diverges, that then the set of infinitely often hitting points has measure 1. So if our dynamical systems satisfies this dichotomy condition here, then we speak of a dynamical Borel-Cantelli lemma. And typically one studies that for, yeah, as I draw in that other picture, kind of a sequence of targets that are balls around a fixed center, and yeah, where then the radius goes to 0. And if our dynamical system satisfies such a dynamical Borel-Cantelli lemma for these nice sequences of balls around a fixed center, then one also says that the dynamical system satisfies or has a monotone shrinking target property. Yeah, so as for this monotone shrinking target property, we restrict ourselves to these nice target sets here. So, and yeah, there is a long list of results on dynamical Borel-Cantelli lemmas in kind of as a rich history. And it has been, or these dynamical Borel-Cantelli lemmas have been proven in various settings of dynamical systems. And yeah, I won't go into the details of these results, but you see that, okay, starting kind of with expanding maps on the interval, up to then, yeah, unausserved diffeomorphisms, and yeah, particularly the work here by Kleinberg and Margulis had kind of, yeah, impact on, or had very important applications to geometry and number theory, particularly on results on simultaneous approximation and Diophantine approximation. And yeah, the general idea is to use the mixing property for a dynamical system, which I wrote here, where yeah, kind of you mimic the independence that you had in probability theory. You now try to mimic that for your dynamical system, so that, okay, if you look at large times, that then, yeah, the measure here converges to the expected thing. So you kind of want to mimic the independence behavior that you had for IID processes in the dynamical Borel-Cantelli lemma. But just mixing is not good enough. So there are counterexamples. Fayad constructed a mixing diffeomorphism that does not have the monotone shrinking target property. So you need kind of mixing with a kind of sufficient speed of getting this limiting behavior. And we will talk later about this kind of speed of mixing and what is necessary to get these dynamical Borel-Cantelli lemmas. Yeah, I want to focus on a stronger version of such dynamical Borel-Cantelli lemmas, namely on so-called eventually always hitting points. So for the dynamical Borel-Cantelli lemmas, we were looking at those points who hit our sequence of targets infinitely many times. Now here we look at those points where there exists a number n, such that after that moment n, your orbit always have to have a hit to the m's target. So we look at the first m iterates of our point x, and among these m iterates, at least one of them has to lie within our target set Bm. So if we write this again in a set theoretic notation, then this already looks a bit more complicated. So here, of course, we take this union to resemble here that we look at the orbit of length m. So that's why we look at these m preimages of our mth target set Bm. And now this fact that, okay, our points here, there should exist an n, such that after that point n in time, we always have a hit in our orbit. So this is why we have to take here then the union and then the intersection. So this becomes a lim-inf set of this union of the preimages. So and this makes the analysis of these sets way more complicated, as we will see later. So on the one hand, I said that this is a stronger property indeed. So if we again look at a nested sequence of shrinking targets, and we remove this set gamma here. So these are those points who, whose orbit kind of has an intersection with this. So here we take the intersection over all our target sets. So you look at those points who basically have hit the center of your target set once. Of course, if they hit this center of your target sequence once, then they will always lie in our set of eventually always hitting points, because then their orbit here always has a non-empty intersection with all the following target sets. So, but since we assume here we have this nested and shrinking sequence whose measures converge to 0, so this intersection here is clearly a set of measures 0. So what we take here is a countable union of sets of measure 0, so that this is a set of measure 0. So, and if we remove this set gamma, then for all the other points in our set of eventually always hitting points, they have to have then automatically infinitely many hits to our sequence of targets. So generally speaking, you could have that maybe you have a very close hit, then you can wait for a long time until you have to have another hit, or your set of eventually always hitting points requires you to have frequent hits to your sequence of shrinking targets. So both of these ways are possible for a point to lie within this set of eventually always hitting points. So, and with a similar proof like the one that I presented you for the hitting infinitely often, one can show that also this set of eventually always hitting points is essentially invariant. So we again get a 0-1 law for ergodic transformations. So then you can ask the same question that we asked for the hitting infinitely often times, namely, okay, under what conditions on the decay rate of our measure of the targets do we have that this set of eventually always hitting points has measure 0 or full measure 1? And in joint work with Maxim Kirsebom and Thomas Persson, we started to investigate that question, and we tried to kind of basically take these techniques that were used in the study of the classical shrinking target problem and try to apply them here for this set of eventually always hitting points. So, and we got some partial results at that point in 2020. that were applicable for very large classes of dynamical systems. But as I will show you later, they were not far from being optimal. But I'm still presenting them here to kind of already show at this stage that, yeah, there is a significant difference between this hitting infinitely often and eventually always hitting. Namely, what we showed that for those systems here that kind of satisfy or have some kind of hitting time statistics, that then if you have a sequence of shrinking targets that are of the form constant over m, that then the set of eventually always hitting points has measure 0. While, of course, for this classical dynamical Borel-Cantelli lemma, if you had a sequence of targets of the form constant over m, okay, the sum is divergent, so the set of infinitely often hitting points had full measure. Well, here we get a set of measure 0. Yeah, no, but yeah, exactly. So, but this works for all sequences of this form. So in particular, if I would take equal to constant over m, then they still satisfy this theorem here. Exactly. And yeah, and this, okay, I won't go into details right now, maybe later. So this is applicable for large classes of dynamical systems, because what we here required is only kind of having this hitting time statistical behavior, and this has been proven for various classes of dynamical systems. In the other direction, to find sufficient conditions for the set of eventually always hitting points to be of full measure, we also try to adapt these techniques from the classical shrinking target problem, and use this, what I at the beginning described as a kind of speed of mixing, and this is typically then referred to as decay of correlation. So if you have some sufficient fast decay of these correlations here, then we could prove sufficient conditions for this set of eventually always hitting points to be of full measure. So if you have here some exponential decay of correlation, then if your targets grow of this form here, or decay in this form here, then this heading eventually always had full measure. While if you only have a polynomial decay of correlation, then you have to change here and have to go to different polynomial law for your decay rate. So let me begin, since I will present new results later, don't touch the detail, but I just want to present these two toy examples to show this kind of gap that we encountered at that point. So we have already talked this morning, mentioned the doubling map as one example of a dynamical system that one can always use as a good toy model. And we look at the doubling map as an interval map, and it has the classical Lebesgue measure as the invariant measure. And we look at a nested sequence of shrinking intervals with a fixed center. Then in this setting, our results gave that if the targets have a decay rate of the form constant over m, then the set of eventually always hitting points has measure 0. While if the decay rate is of this form, then hitting eventually always has measure 1. Around the same time, another group of people, Kleinburg, Konstantulas, Richter, also studied this concept of eventually always hitting points. And I also present one toy example of their work. Kind of, okay, here we chose a symbolic way to describe the map. So we have the shift space, and the transformation is a left shift. And as the invariant measure, we take here the 1/2, 1/2 Bernoulli measure. And then they had to look at nice target sets, namely nice cylinders of this form here, where your first entries are 0. So you look at cylinders where first km entries of your sequence are 0. And then they got very tight conditioned. So if the measure decays of the form 2 times log m over m, then hitting eventually always has measure 0. While if you have here decay rate of the form constant, with a constant larger than 2 times log m over m, then hitting eventually always has measure 1. So these conditions are, already quite tight, but still it's not a dichotomy condition, because on the one hand you could have some fluctuation in your sequence, or you could ask about what is about 2 times log n times log m. So there are a couple of sequence of targets where you cannot make any, or they cannot make any conclusions. So in general, between these works of Kleinbock, Konstantulas, Richter, they got preciser or tighter conditions, but they only worked for specific target sets and restricted family of dynamical systems, while our conditions were, they had a broad gap of sequences where we couldn't say anything, but they were applicable for more general targets and vast classes of dynamical systems. But nevertheless, both results were very unsatisfactory because we didn't have any dichotomy condition. So, okay, it proved then useful to rewrite this whole problem and used a more statistical approach to this whole question on dichotomy conditions for eventually always hitting points. And so we consider here a function psi that should be decreasing, and that if we approach 0, then it should go to infinity. So you could just think of 1 over y or negative logarithm of y. So these are nice observables here that we could take. And then we fix a point x tilde. This will later play, as in our eventually always hitting problem, the role of the center. And we define the observable phi, which looks at, here's the distance of your point x to our fixed center x tilde. And then you apply this function psi here. And this gives us a stationary stochastic process defined as the kind of the sequence of observations along our dynamical system T. And we associate to this stochastic process its maximum process. So we look at the maximum of the first n observations. Then, in this notation, the set of points whose nth iterate lies in this nth ball corresponds to the event that, our observation xn is larger than un, where un is exactly given by psi of our radius Rn. And the event that our maximum process is as most un clearly corresponds to the intersection that all the first n observations are at most un. So with this setting, now we can write the set of eventually always hitting points as follows. This was our set theoretic notation that I deduced earlier. So we have this lim-inf set of this form here. So here our case pre-image of the m's target. This is exactly, as we wrote here, corresponds to this event that xk is larger than um. So now I take the complement So it takes a complement. So I get here an intersection over the set of that the process xk is at most un. And here we said that this corresponds to the maximum is at most um. And now since I take the complement, I have that the maximum is larger than um. And in statistics, this is denoted as, that eventually is larger than um. Our maximum process, is above this threshold um. So we have rewritten our question of this eventually always hitting points in the framework of what is called statistical extreme value theory. So this is a branch of statistics that, looks at the stationary stochastic process and its associated maximum process. And extreme value theory is based on understanding the limiting behavior of this maximum process, either in distribution or in the almost sure growth rate of this maximum process. And one says that one has such an extreme value law for this maximum process Mn if there is a non-degenerate distribution function H, such that for every tau, if there is such a sequence of levels un, such that n times the measure of x1 is larger than un, converges to this level tau, that then we have here the convergence of the measure that the maximum process is at most un, converges to this value here. And this is kind of motivated by the IID case. So in the IID case, the measure of that the maximum is at most un corresponds to, you look at the complement, namely that you were larger than un. And since we are in the IID case, this is equal to then taking here the mth power of this one here. And to kind of relate it to our condition here, we write it this way. So now this one goes to tau, and our whole expression here converges to the exponential of negative tau. So we get here kind of such an extreme value law and have the standard exponential distribution function as our distribution function. So, extreme value theory itself is kind of has also a wide range of application. And one example from reality relates to first here to the Netherlands and the kind of the sea level. So about 40% of the Netherlands is below the sea level. So the Dutch government has decided that the probability of a flood, so that the sea levels exceed the height of the dikes in a given year, should be at most 10 to the negative 4. So the question is, how high should the dikes be? And extreme value theory can be used to answer this kind of question. So it's, if you refer to Wikipedia, then it says extreme value theory is a branch of statistics dealing with the extreme deviations from the median of probability distribution. It seeks to access from a given ordered sample of a given random variable the probability of events that are more extreme than previously observed. So it's kind of, you try to estimate the probability of events that are more extreme than things that you have ever recorded, which on the one hand sounds a bit obscure because normally in probability you look at the number of events you have observed and then make a guess for the future. But now here you're dealing with events that are more extreme than things that you have ever observed. But you kind of, this approach of then kind of looking at or making an estimate on the distribution function and then their tails, gives you an approach to study those extreme or rare events. And yeah, of course, this has applications in many disciplines. So yeah, classical extreme value theory is then based on finding the distributional behavior of this maximum process. So you typically try to find this kind of scaling sequences AN and BN, such that you get convergence to a non-degenerate distribution function. And for IID processes, it's a classical result that only these three types of distribution functions can occur. And of course, that is then very useful in modeling, because then you look, okay, what is expected tail behavior, and then you choose the associated distribution function. And so if one now wants to go to the dependent case, then again, the kind of philosophy is to say that asymptotically independent sequences behave like IID processes from the perspective of extreme value theory. So you again impose here some condition on the kind of asymptotical independence. Namely, okay, if we look here at the intersection of the events, that xi is at most r and xj is at most r, and I and j are apart from each other, then you should basically see the independent behavior. So, and so I won't touch the details here, but then the approach is again to use this kind of almost independent condition, this condition here, and then a condition on so-called short return times. And if those conditions are satisfied, then one could show that actually even for the stationary stochastic processes, if we have such a sequence that satisfies these two conditions, then we have the same limiting behavior as for the IID case. And in the recent decade, there has been great progress on kind of taking those or adapting those results and transfer them to the setting of dynamical systems. So to replace this condition D and D prime by weaker assumptions and mixing conditions on the dynamical systems. And yeah, so then that way one could prove extreme value laws for, again, large classes of dynamical system. And yeah, this is a good monograph, and there's a lot of references on results on these different kinds of systems. The extreme value laws have been proven. For our talk today, or for this problem on the eventually always hitting points, we are not that interested in the convergence in distribution, but we want to estimate the almost sure growth rate of this maximum process. So a fundamental problem is to determine optimal bounding sequences UN and Vn, such that almost surely there exists an n, such that after this point n, our maximum process lies between these two bounds Vn and Un. And here again, as for the eventually always sitting points, this number n here can depend on the point x. So, and we want to study this almost sure growth rate for the maximum process, and then find a dichotomy condition for our sets of eventually always sitting points that we rewrote in this statistical manner. So, and this rewriting and looking at it from that perspective was very useful to in the first get an idea of what could be the appropriate dichotomy condition. Namely, in the setting of IID processes, there is a result by class here that kind of gave a dichotomy condition for the for the growth rate, so that this mn larger than un eventually has either measure 0 or measure 1. And yeah, I wrote this result here. And now for our dynamical application in mind, we kind of, okay, the probability of that x1 is larger than un corresponded to the measure of our target set, of the nth target set, where un was related to the Rn by our function psi. And yeah, the probability of this, that the maximum process eventually is larger than un, that one corresponded to the measure of the eventually always hitting points. So yeah, this clearly here was give us the idea what to look for as a kind of dichotomy condition for the eventually always hitting points. And in joint work with Mark Holland, Maxim Kurzebom, and Thomas Persson, we could then prove such a dichotomy condition for the eventually always hitting points. And then at the same point of time, this is a result on the almost sure growth rate of such a maximum process in a dynamical systems setting. And yeah, for the presentation, let me keep it to, or restrict it to this following. So we have a piecewise expanding interval map with an ergodic measure, which is absolutely continuous with respect to Lebesgue. So if you remember when I talked about these dynamical Borel-Cantelli lemmas, yeah, the first one was also proven in this setting of piecewise expanding interval maps. So this is clearly a good starting place to look for results. And yeah, then we have this setting that I described. So this statistical framework of looking at such an observable phi that is related to the distance to the center via some function psi of our form. So where you could think of 1 over y. And we have a sequence of radii such that this expression here is non-decreasing. In particular, I mean, it's clear that the measure of the targets is diverging. So from the point of view of hitting infinitely often, yes, we will hit this sequence of targets infinitely often. And then here we have a kind of technical condition, which I guess you can ignore at this moment because it's only relevant in case that this measure mu is very degenerate in the sense that it gives value to a lot of value to particular regions, because otherwise kind of this condition here will already require that our sequence of radii cannot decay exponentially fast. So, and then we get this analogous dichotomy condition. So the result by class, namely if our sequence of radii satisfies that this sum converges, then the set of eventually always hitting points has measure 1, while if the sequence of radii satisfies that this sum here diverges, then the set of eventually always hitting points has measure 0. So this is really kind of the analog to this result by class that is referred to as the Robin-Zygmund series condition. So now we have the analogous criterion in the setting of dynamical systems. And yeah, to show you one example of such an application is kind of we can apply the result on the Gauss map, and this will give us results on the almost sure growth rate of the coefficients in the continued fraction expansion. So yeah, the Gauss map I wrote here, and it has an ergodic invariant measure with a density function written here. And so we can take the observable psi of this form with a fixed center x tilde, so that, okay, if we look at this continued fraction expansion of your point x, you have here these coefficients ak, then they kind of can be read off via our observable function psi under the iterates of the Gauss map. And then our results allows us to obtain a dichotomy result on the almost sure growth rate of this continued fraction expansion coefficients. Namely that kind of for mu almost all x, that the growth rate is of this form that, okay, here we get this log n over n, and here the value 1 over log 2. Then let me also show you an example where this Robin-Sigmund series criterion does not hold, and we get a different dichotomy condition in a dynamical setting. And this, in the statistical framework, this is referred to as clustering effects and extremal index. So under clustering of extremes, one understands that, okay, especially if you look at floodings and so on, that you might have extreme values very next to each other, because if you think of flooding, then it's still that there was a lot of water around, maybe the ground is still muddy and so on. So it is more likely of having a flood next to a previous one than all of a sudden. So, and this is referred as, so that you have consecutive occurrences of exceedances of a given threshold. So you have extremes clustered. And then one says that such a stochastic process has an extremal index. If we have an extreme value law for our maximum process that does not converge to the exponential function itself, but kind of rescaled with this extremal index theta. So this extremal index theta quantifies the intensity of clustering. So, okay, if theta is equal to 1, then we are basically in the setting of the IID case that I showed you earlier, that then we would converge to the exponential of negative tau. But if we have a small values of theta, then this kind of refers to a long memory of your process, where you can interpret 1 over theta as a mean size of the clusters. Okay. And in dynamics, such a non-trivial extremal index can happen for a sequence of shrinking targets that limits onto a periodic point. Namely, if we, again, to rewrite it in this statistical framework, we look at a Q periodic point of our map T. And again, we have this observable that looks at the distance to this center x tilde, which is now our periodic point. And we again look at these events here. On the one hand, that we hit the ball around x tilde of radius Rn. And here we look at these that do not have a hit over these Q iterates here. Yeah, so our set here gives the points in UN that do not return to our ball within the Q iterates. And then, okay, if we look at this proportion here, this is then the proportion of points in our ball that do not return within Q iterates. So when this limit exists, then this limit theta takes the role as an extremal index. So for example, if we look at a hyperbolic repelling Q periodic point for a piecewise expanding map, and mu is a Lebesgue measure, then we get this expression here for the extremal index. So for instance, we looked at the doubling map and at the point 0, this is a periodic point of period 1. So this will have then, and the derivative is always 2. So it has extremal index 1/2. That's, by the way, why in that result by Kleinburg, Konstantulas, Richter, they had this break was at 2 times log n over n. So this 2 refer, or kind of you can find it then again here by the fact that here now the extremal index is 1/2. And yeah, so if we look at such a, now our setting again of a piecewise expanding interval map with an ergodic measure, which is absolutely continuous with respect to Lebesgue. And again, we have this observable function, but now compared to the previous result, we look at the hyperbolic periodic point of period Q, whose derivative here is finite. And again, we look at the sequence of targets at around this fixed center, which is that periodic point. Then we, and okay, we also have to assume that this sequence of theta ends indeed converges to this, to a value theta, and that this convergence happens at least with this kind of speed. Then we get a dichotomy condition with including, or that takes into account this extremal index. So we get a dichotomy condition that is different from the Robin-Siegmund series criterion for IID processes, but now, yeah, looking or taking into account this extremal index. And yeah, as far as I know, this is something that even hasn't been studied in the setting of stationary processes that much. So it would be, or it's an interesting question, to which extent similar conditions hold in the setting of general stationary processes, and yeah, what are conditions there that you have to impose to get a similar criterion than this one. So this kind of shows this interplay between, okay, clearly we only had a chance to approach these problems from getting this insight from extreme value theory and statistics to first get an idea of what a good condition could be. And on the other hand, now this kind of dynamical framework also shows maybe some, or puts some new significance or importance to study some questions in probability theory for general stationary stochastic processes. And of course, also within the proofs, a lot of these techniques were based on looking at these proofs in the IID case and try to modify and adapt them to our dynamical setting. So I don't know, how much time do I have? 5 minutes. Okay. So then very briefly, I will just say that, okay, kind of how we approach it is, of course, to find dynamical analogs or versions of these conditions that are earlier denoted as D and D prime. So on the one hand, there was this D condition gave you this asymptotically independent behavior. So to resemble that, we impose some condition on the decay of correlation. So we need to have fast decay of correlation. In fact, we need exponential decay of correlation. So this is kind of to resemble this condition D. And then there was this condition D prime that was relating to short return times. And already that condition was rather technical, so I didn't go into the details at all at this point, and I will also skip them here, but just to point out that, okay, this kind of here resembles, again, you look at returns to your set, to your ball here, for some kind of short times, short compared to the whole time window of length n, because here we look at then time up to ns, where s is less than 1. So that's why kind of this is referred to as short return time estimates. So, and then we kind of use these two as a kind of to mimic this condition D and D prime that I mentioned in these approaches to transfer extreme value laws from IID to stationary processes. And now we use approaches like these to transfer them further to the dynamical setting. And yeah, I'm afraid to go into the details. I would need 2 more talks, so I better stop here and give you time for questions.
I actually have a question about how fragile or how strong are the proofs with respect to rescaling of your n, because in principle you can always choose subsequences and see if the theorems still hold or don't hold, or they change from one to the other. And I was wondering if you have any insight into that, because when you move
okay, so you want to look at hits not along all times, but maybe only at powers of 2 or
yes.
n square or something.
Exactly.
Yes, no, I mean, these results are very fragile. So I mean, we haven't given any thought about looking at specific subsequences. And yeah, I right now I wouldn't have much hope that one could extend this thing to specific or along specific sequences.
Any other comments, questions? So let's thank the speaker again.
So thanks a lot. Thanks for inviting me. And so I was not really sure, again, like Caroline, about the public. So I'll start by some very basic thing. So since it is just after lunch, you can sleep if you know everything. So what about, okay. So let me start with some simple things, simple object, which is some topological dynamical system. Okay, so a topological dynamical system is just, I will talk always in discrete time, not because I think that discrete time is particularly relevant, but because simpler are just simpler. So most of the things that I am saying in discrete time, they hold in continuous time, but there is always some extra difficulties that maybe I will mention later on. But for the time being, I just consider discrete time dynamical system. So it is just some set, some topological space and some map. And in fact, the map, if the map is continuous, which is not always the case, because there are interesting examples in which the map is not continuous, but okay, just to fix idea. Then you want to discuss things like the thing that Caroline was discussing this morning, and the issue is that you would like to have a measurable dynamical system. So in order to have a measurable dynamical system, you need other 2 objects, which is a sigma algebra and an invariant measure. So this one is just a sigma algebra on M. This is easy to produce. Just take Borel. So you just take the sigma algebra generated by the open sets. So that is more or less obvious what you have to do. But the issue is that what do you put there, right? So in general, there are certain cases in which also you don't have any choice, right? For example, you can have the situation in which you have M, sorry. You can have M equal T1, the one-dimensional torus, and T of X equal X plus omega mod 1, and omega is not a rational number. Okay, so this omega, let's say it is in 0, 1, but not rational, then this system has a unique invariant measure, which is Lebesgue. So you don't have much choice. So there's only one invariant measure, that is the one that you have to put over there. But the system, so systems that have only one invariant measure are called uniquely ergodic, maybe, but I think so. And they exist, like this is an example. I mean, you can do it also on higher dimensional torus. Another example which is very relevant is horocycle flow on manifold and negative curvature. So there are such systems, but they are rather special. I mean, so the system that I will discuss in this lectures are systems in which there are typically a lot of invariant measures. In particular, systems that have some form of hyperbolicity. So that is what I would like to talk today, say 2 words, just in case some of you don't know very well about hyperbolic system, just 2 words about that. So just let me remind to you, so because the first question, of course, that you have is that, but does it always exist an invariant measure? So that in this case, of course, you have to be, first of all, let me say that in this course, I will be interested in this one. I want a probability measure. So not because I mean, sigma finite measures are irrelevant. There are many situations in which sigma finite measures are relevant, but this again adds an extra layer of complexity. So if you want to know something, there is a book of Aronson about systems that have infinite measures. But probability, if the measure is finite, meaning finite that mu of m it is finite, then you can always have it a probability measure, just rescaling it, so just normalizing it properly. So that is okay. And so this is what I will discuss. And also, just to make things simpler, let me take this compact. Also, non-compact case, there are a lot of relevant cases in which M is not compact, but again, let's keep these things simpler. So in this case, then the answer is that an invariant measure always exists, and the argument is essentially due to Krylov-Bogolyubov. Probably all of you know it, but just to remind you how the idea works, because it's kind of a very nice idea. The idea is that, first of all, well, that is kind of a point of view that has been developed starting with the Russian school. So you have a dynamical system, and the dynamics is, of course, given by the iteration of the map. So as we saw this morning, this is a trajectory, is a future trajectory. And so that's what people used to study, right? I mean, just the trajectory, what the trajectory do, and so on and so forth. This idea instead that started essentially maybe with Kolmogorov, well, before actually with, I don't know, it's debatable, right? Because still, for example, Birkhoff or Neumann, they were thinking more about trajectory, even when they were looking at dynamical system. I mean, it's a subtlety, but I think that maybe Kolmogorov was the first one that really saw that maybe it's a good idea to look at the evolution of measures rather than of points. So the evolution of measure, how do you define the evolution of a measure? Well, you just define T star M of a set A as mu of T minus 1 of A. Okay, so in this case, if mu is invariant, then this is just mu again, right? So the being invariant simply means that T mu is equal to mu. So, but this, you can do it for any, so since I use mu for an invariant measure, let me use nu for any other measure. So if you take any measure, you can define is push forward. And this creates, so if you take the space of probability measures, T star is a map from the space of probability measures to itself. So now you have taken your dynamical system that acts on point of M, and you have glorified it to a dynamical system that acts on the probability measures on the space M. And of course, if you never saw that, the first idea is that this is a totally idiotic idea, right? Because you had some nice dynamics on maybe on a finite dimensional space, and now you end up with dynamics in an infinite dimensional space, which is the space of probability measures. It's absurd, but there is a big advantage, and the big advantage is that typically this guy is non-linear, but this guy is linear. And this is well known that in mathematics there are many, many situations in which you trade non-linearity with infinite dimension and but linear, and you gain, because somewhat it is easier to treat an infinite dimension, or in many cases easier to treat an infinite dimensional problem using linearity than to study something finite dimensional but non-linear. So that is kind of the gain that you have. And then if you think of this as a dynamical system, the first question that you ask yourself about a dynamical system is, what are the invariant measures? And so you want to solve this equation. So that is like to find a fixed point, right? So that is very natural now to study this problem. And the idea that goes back to Krylov-Bogolyubov is just to study, well, it's very similar to what Caroline wrote today, but it was about, today it was about the trajectory, and here is about the measure. Just take the trajectory of the measure and you take the average. And this is a probability measure. So it is the probability measure are the measures that, of course, are in the space of measures, this guy is weakly compact. So it's a weakly compact set. And so it has accumulation points. And the accumulation points, so this has subsequences that converge to some measure mu. And this measure mu is invariant. And you can easily check. It's kind of trivial. All right. So this is a way to construct invariant measures. That's very simple idea. But as you see, it is a little bit worrisome because this guy is completely arbitrary. You can start from whatever you want, and it will converge to something. So you can produce bazillion of invariant measures in such a way. And that, it's at the beginning, is a topological dynamical system. Yes, you are right. If it is not continuous, and then compact, yes. Yeah, that's right. And that's good to remark it. And if T is not continuous, you can still do this argument asking that you can somewhat do something still. But it requires a little bit more of care, so I don't want to talk about it. Okay, so now you have a mechanism somewhat that produce invariant measure. The problem is that they may be kind of really stupid, right? Because, for example, imagine that you have a periodic orbit, So you have a periodic orbit here. Okay, so this is x naught, this is x1, and so on and so forth, and this is equal to Tp x0. So this is a periodic orbit of period P. And then imagine that you start with nu equal the delta on the point x naught. And then what are you going to get? Then mu is going to be equal to 1 over P, the sum from K that goes from 0 up to P minus 1 of delta xk. Okay, where xk okay, and so it's just this is an invariant measure. Every point in the orbit has a weight that is 1 over P. So okay, fine, but this is not really what we are looking for in some sense, right? We want invariant measures that have something to do with the statistical properties of the system, and this doesn't see much of the system, right? It just sees that particular periodic orbit. It doesn't know anything about the rest of the system. So the question is, which kind of measure are we interested in? In some sense, we are not interested in all the measure. We want measures that, you know, have something to do. And now with the somewhat physically relevant question, at least that's my point of view. So this is a kind of, yeah, I agree with what Caroline said this morning. It's kind of philosophical question, right? Because you can spend, I could spend essentially the rest of all of my time, not of today, but of all the week, discussing about what measures are relevant and why are relevant, and I will not convince you, but what is worse, I will not convince myself. So because I tried already to make some you know, I missed the word in English, to clarify my mind, and I failed miserably. So I'm confused myself about this issue. So better that I don't talk about it. But there are certain class of measures that are certainly relevant, and these are, for example, what was already mentioned this morning, like physical measure. So for me, a physical measure, it is a measure. I mean, you can define it in many ways, but my point of view is that is a measure in which nu is absolutely continuous with respect Liouville or Lebesgue, if you want. So to make sense of it, of course, you need some structure here. So this is a compact Riemannian manifold. And now, if it is a compact Riemannian manifold, it has a natural volume, and this I call Lebesgue. I mean, it's debatable if you want to call it Lebesgue, but I mean, it's the volume of the Riemannian manifold. Okay, so you start with these measures, and now you want to know what you get. Okay, so if you start with a measure like that, then at least this measure will capture some basic statistical properties. For example, a quantity that you are certainly interested in is, for example, you have phi composed Tn times G, and then you integrate it in the X, where this is the Riemannian volume, and you want to know what happened to this quantity. This is a quantity that physicists like this is something that you can compute. It has to do with the correlation of two observables. So, so you can interpret this as a correlation. Also, you can interpret this as if you have that G is positive and the integral of G is 1, then you can interpret this as an initial measure. And then if this is the initial, so this you can call it d nu. And then just by changing variable, this stuff here, it is equal to the integral on m of phi with respect to d t n star nu. So just because of the definition of, well, here, this definition implies that for each phi continuous, you have that t star nu of phi, and by this is a notation I will use often. This means that is the integral of phi with respect to t star nu, and this is equal to nu of phi composed t. Okay, so that is kind of, this is equivalent definition. Okay, this is on set, and this one is on functions, on averages. So from this, it follows this. And that means that, I mean, you are just looking at this quantity. So what is the distribution of your system at time n? And you want to take the average of a function. So that means that you are just studying this measure. Okay, so, sorry. So in order to study this, of course, you want to know a little bit more, right? I mean, already you see that if I study if this one is absolutely continuous with respect to, let's call M. Where did I write it? Let's call M the volume measure. So if I am so crazy to take just a continuous dynamical system, then it is not obvious that this thing is absolutely continuous with the volume, right? I mean, this, okay, you can study system like this, but I mean, you make your life harder. So let's say that this is absolutely continuous with respect to the volume, which means that T is non-singular, and this one will be some Jacobian, right? I mean, which I can call it dt. This is just the Radon-Nikodym derivative. Let me call it dt. If T is differentiable, then that is the formula. I mean, this is the determinant, I mean, actually, it's the Jacobian. So this is actually the determinant of dt, actually is the absolute value of the determinant. Okay, so that is the Jacobian. Okay, and in general, if you have a map T, you can just say, okay, but what about I want did I write it correctly? Yeah, I'm not so sure that this formula is true. Let me just compute it, so I will. Yeah, sorry, this is Tm. Okay, so right. In general, I want to compute if I have nu that is equal to d to h m. So this is absolutely continuous with respect to Lebesgue, and this is the Radon-Nikodym derivative. Then I want to know what this guy will look like. And this turned out to be some operator of H, which in general, if you compute it, I mean, it's a computation that probably all of you know, but if you don't know it, you can just compute it by yourself. And that is the formula. Yeah, maybe I have a -1. I'm not sure, because if this is 1, then this has a -1. Okay. And there is a sum. I mean, this is a formula that is true if you don't have any pre-images, right? But if you have pre-images, then you have these formulas. If you have only one, if this is invertible, then it's the formula, right? But if it is not invertible, this formula is not true. The formula is that you have to sum over the pre-images. I mean, it's just a change of variable. Just do it by yourself, and that is what happens. I mean, you can do it in. So, okay. So this guy here is called the transfer operator. And it is, so it has the property that the integral of phi composed T H dm, so this one now is equal to phi of d T star of H m, but the Radon-Nikodym derivative is given by this, and so this is just phi L H dm. Okay, so you see from this formula that if you are in L2, this guy is just the transpose of the composition with the map. The composition with the map is called the Koopman operator. Okay, so this one is a guy that was around for a very long time. For example, if you know the proof of what is called ergodic theorem by von Neumann, which is a proof in L2 versus the proof by Birkhoff, that is an almost sure result. And for Neumann studies exactly this operator. And that is more or less the first time in which I have used the I have seen the use of operators in dynamical system in this way. I think that it was really, in some sense, well, Koopman used them, but to see that this was a really good way of studying a system, that in some sense is for Neumann. And so there are reasons why, of course, if the map is invertible, then this guy here is simply the composition with the inverse. And if the map is symplectic, then the determinant is 1, and then it is just the composition with the inverse. So there is not much difference. Like you compose with the map, you compose with the inverse, who cares? But if the map is not invertible, then you have this formula here that turn out in many cases to be much simpler to study than this guy. So then, I mean, that is history, right? Now, in some sense, it doesn't make any difference. We know how to study directly this guy also if we want, but it turned out that this is easier. It's easier to study. For you can do whatever you want, but that is convenient somewhat. Okay, so fine. Up to now, I'm just probably boring you to tears. So let me say something else that I'm sure you all know already anyhow. So the point is that if you want to study what happens to this operator, so the point is that you want to see, if you want to study things of this type, you want to study what happens when you push forward the measure, and this is exactly the same in this case than looking at this object here, right? So you want to look at iterate of this operator and understand what happened to them. And if you understand that, then you can kind of compute all kinds of things. Now, the problem is that if you want to understand this operator, typically, I mean, some things are true always. For example, this L is a contraction in L1. This is kind of trivial, right? Because if you do LH and you look at the L1 norm, this is the integral of LH of x dm or dx. If you let me write dx, just this is the volume. So let me just be sloppy. It's faster to write. So then this L is a sum, so this is less or equal than LH of x dx. That's triangular inequality. And now this is equal to the integral of h, and then you can put a 1 here. You multiply by 1. Okay, that's innocuous. But then you can use the formulas over there, and this is equal to say 1 composed t times h of x dx, but 1 you can compose it with whatever you want, is always 1, and so this is equal to h dx, which is the L1 norm of h. So that's more or less always true. L is always a contraction in L1. Okay, fine, that's nice, but and if you want, maybe you can get some estimate in LP, but you don't do much with that, right? You just say that, okay, it doesn't grow. Well, nice, it doesn't grow. Because it should not grow. It should send probability measure into probability measures. So it's a positive operator, by the way, right? If H is positive, then LH is positive, right? Which means that the density gets mapped into a density, right? Because if you have a density of a probability measure, it has integral 1 and is positive. So LH is also a probability measure, should have density integral 1 and be positive. So that's kind of trivial. But you can not squeeze much out of this. Because, okay, you can have a series of probability measures that converge to a delta function, for example. So you, for example, if you want to do Krylov-Bogoliubov, you don't know much. I mean, in order to do something, you need to have more information about the map. So that is the cars of this thing, that we can say a lot of things about very few examples. That is the truth, unfortunately, right? The general dynamical system, there are a bazillion of type of dynamical system, and for essentially almost all of them, we can say essentially nothing. But the one for which we can say something, they have all special properties. And in this case, let me just say that let me just take the simplest possible example. Simple possible example is that M is TD and T is C2 of TD, and let's say that DT minus 1, it is smaller or equal than lambda smaller than 1. So this is an expanding map of the torus, d-dimensional torus. This is the easiest case that one can try to understand. If you cannot understand this, then forget the rest. Okay, so that is the first thing I would like to discuss. And what can you say in this case? Well, what can you say in this case is the following. You can take a derivative. Well, now the map is, so you can say, okay, let me restrict to H that is differentiable. And now I'm going to take the derivative with respect to xi of LH of x. And you can do this computation. And this computation is, first of all, notice that the determinant of this guy is invertible, right, in particular. So it means that the determinant is never 0. So it means that in this formula, this guy is either always positive or always negative. So let me just say that it's always positive. So I can take away the absolute value since it's always positive. Okay, fine. Then since it was always positive, I can say fine. I can take the derivative here. So let's say this is the, I have y that belongs to t minus 1 of x. And then I have, so I want to take derivative, right? So first I can take derivative. I have h and I have the determinant of dt, okay, on in point y. And and I want to take the derivative of this thing. So the first thing that happen, I can take the derivative with respect to x k of this, and then I have the derivative of x k with respect to xi, and then on the other hand, I can take the derivative of the denominator and this instead is h of y, and here I have the derivative of the determinant of dt y with respect to x k, and then I have the derivative of x k with respect to x I. Okay, that's an explicit formula that you may like it or may not like it. This guy here, it is the sorry, this is y, not, I'm sorry, y. Because you take, this is just the derivative, well, I mean, I call it x, but I mean, okay, fine, let's call it y. The problem when you do derivative of, it's the same problem in partial differential equation. When you start to take derivative, and you have to kind of interpret them with a grain of salt, because if you try to write everything precisely, you go crazy. I mean, so anyhow, this means just the derivative with respect to the kth coordinate of y, of h. All right, and now this guy here, what is the derivative of yk with respect to xi? Well, this is simply the derivative of dt minus 1 component ki, something like that. Just the inverse. And so this guy, I know that is smaller than lambda, which is smaller than 1. So it means that this term here is multiplied by something that is smaller than 1 in NOR. So that means that if I take the gradient of LH and then I take the L1 norm, this is less or equal than what? Well, this is this matrix multiplied by this guy here. So that is just the integral. This part here, you see, is simply L. So this is the absolute value of L. And then you have dt minus 1 gradient of H plus, and then you have this stuff here. And that stuff here, what it is? Well, this is going to be, again, LH, which is H and minus 1 of this. And then here you have another determinant of dt minus 1. And you put all this stuff here together and you give it a name. You call it, I don't know, B. It's just the distortion. It's called the distortion. It's a function. You don't care what it is because this is C2, right? So this is finite, some bounded object, because T you take two derivatives. So this is C2. So this is some function, which is bounded in L infinity. So this B belongs to L infinity. Okay, so that is fine. And now you can just use the fact that you have a contraction. So this is less or equal. You have a contraction in L1, and this tells you, and this guy is smaller than lambda, and this tells you that this is smaller than lambda, H L1 plus some function time, oh, sorry, gradient of H, and this L1, okay? So you get this inequality. Sorry, what? Oh, I had already put them on the, sorry. I'm sorry. Yeah, they are already at the denominator. They don't need a -1. I mean, apologies. Here there was not, right? Yeah, there are two. Yeah, because there was a square, right? But I split it because this I want to put it with this guy. So I reproduce the transfer operator. Yeah. This one has no square because I take the derivative of the numerator, right? This has the square because I took the derivative of the denominator. And I want to just say this is some function that I call B, and this is just the transfer operator. So yeah, it's okay. Did I do another mistake? I don't know. You seem puzzled. No. Yeah, but yes, but in the one-dimensional case, it comes from this guy, right? Because this is one, but now it's a little bit different because this has the determinant, this has not, but this is again dt -1. Yes. So if in the one-dimensional case, you will give you 1 over f prime square. Yeah, but I don't know why I did it in higher dimension. I'm sorry, just to try to confuse you. I mean, okay, because probably the computation in one dimension, everybody saw it already, right? But in higher dimension, it's exactly the same. But I mean, so maybe you see it in higher dimension for once. Okay. And now that you have this, you can say, that's interesting. So let me collect this thing. And this normally is what people call the Lazotta-York inequality. Or, what do they, double inverted. Yeah, this is the French version. Do we have some French here? Yeah, so sorry, apologies. Yeah. Okay. So good. And you can say, okay, fine, but who cares? Well, the point is that, you see, now you can start an whole business. I mean, once you have these, you have all kind of property follow. But just to tell you why this is very nice, let's look again at our Krylov-Bogolyubov argument. Krylov-Bogolyubov argument, I can say, okay, fine. Now, instead of looking at the average of the measure, I can look at the average of the density of the measure. So I start with a measure that is absolutely continuous with respect to Lebesgue, with density H. Then I know that the density of the push-forward measure is given by LKH, and I take the average of this. And can I do Krylov-Bogolyubov again? Well, yes. Why? Because if I assume that H is in W11, what does it mean, W11? it means that the W11 norm is the Sobolev space 1,1 is simply the L1 norm of the function plus the L1 norm of the gradient of the function. So this is what the Sobolev space W11 looks like. And now we just see from this that we get control on the W11 norm, because the W11 norm will not increase, because this part will not increase, and the gradient also will not increase because of this lambda, which is smaller than 1. And so now I can say, wait a second, let's compute the W11 norm of this guy. Well, this is less or equal, so there are two parts. I have to take the L1 norm, but that is a contraction, so this is just HL1, okay, plus, and then I have to take the sum from k, from 1 over n, from k to 0 to n minus 1, of the gradient of LKH in L1. But now I can use that inequality. And this, the important thing is that this inequality can be iterated, right? Because if here you have the square, for example, then you can just imagine that L is, so actually you can write it like this. Okay, because I apply L to L of H. So I apply the same formula and I get that, and this I get the gradient of L H, L1, and this is a contraction. And now I can apply the formula again to this term. And so I will get lambda square H gradient L1 plus lambda minus 1 plus 1 B infinity H L1. It's just iterate, and you can keep iterating. And so it happens that you can estimate this part by and then here you have L minus K gradient of H L1 plus, and then you have lambda minus K plus 1 plus lambda minus K, no, what is it? Yeah, plus 1 plus 2 plus 1 B infinity, and then H L1. Sorry, you were saying? I'm sorry. Shit. In my mind, the lambda is always bigger than 1, and this creates horrible problems. I'm sorry, minus 2, and so on and so forth. And this is plus. Sorry. That's when you are used to something, then you try to change it, but your brain resists desperately. And okay, so anyhow, so this is a geometric sum. So this is bounded. And then you divide by 1 over n. So this is something that remains bounded. This goes to 0. So all this stuff is actually smaller than some constant time h W11. So it means that this the norm W11 of this stuff remains bounded forever, uniformly bounded. And now you can play Krylov-Bogolyubov again, but before you were using compactness, and the compactness that you were using was the fact that the probability measures are weakly compact in the space of measure. But now you have another compactness. This is a ball in W11 is compact in L1. And that means that you have subsequences that converge in L1. And so it means that you will have 1 over nj sum from k that goes from 0 to nj minus 1 lkh. This will converge to some stuff, h star. And that is an invariant density because we'll have the property exactly like in Krylov-Bogolyubov. I'm sorry. That this is equal to h star. And so you get that there is a density that is invariant for the transfer operator. And that means that the associated measure is a measure that is invariant. So you have found an invariant measure that is absolutely continuous with respect to Lebesgue. So that is, of course, you can get much more out of this. Maybe I will just, let me see. I forgot. How much time do I have to talk? I'm sorry. It's just 1 hour or more? 1 hour and a half. Oh, holy cow. Okay, fine. No, let's go on. If I stop, I'm sorry. I'm a little bit disconnected because I'm under jet lag. If I stop, I will fall asleep. So I don't want to stop. Okay. So all right. Now. So this was just, I mean, I did all the computation for you just to show you that this very basic idea of taking average and so on and so forth has at its heart some compactness argument, but the compactness you can get it with respect to different topologies. So if you get compactness with respect to a topology that ensures that the measure keep having a density that you like, then you get more information. For example, in this case, we just proved that there is an invariant measure that is absolutely continuous with respect to Lebesgue. In fact, maybe, okay, I want, maybe here. In fact, in this particular case, once you get this type of inequalities, and if you have, so there is an abstract theorem, there are many versions of it, but the one that somewhat people use mostly these days is the so-called is due to Enion. It used to be, people used to use before some theorem due to Turcea and Marinescu. The difference is, I forgot, what is the difference? Yes, there is some difference. This one is more convenient, but I always forget what was the thing that it was not convenient in this previous. Yeah, there was an extra hypothesis that you had to check that in fact is not necessary to check, but now I forgot exactly what it was. In any case, so this Enion theorem, it is just some abstract theorem that says if you have two Banach spaces, B1, normally they are called B and B weak and B. B weak contains B, and an operator L that goes to B weak to itself, and it has the property that L restricted to B belongs is a bounded operator from B to B. I mean, there is a, yeah, I mean, there is a slightly more general version due to Guzel, but let's just stick to this one. And then you have something like this Lasota-York inequalities. This in particular is not really necessary, but I mean, that's what Guzel, you can substitute it with some Weak means that is the norm associated to this Banach space. Okay, so this is, if you put m equal 1 and c equal 1, is exactly what I wrote over there. Okay, so this is slightly more general, but I mean, that is okay. Then, and so these are the equivalent of these Lasota-York inequalities, which is exactly what we proved over there. W weak will be L1 over there, and this strong norm will be the norm in the Sobolev space W11, in which you control also the gradient of the derivative. And and also you need that the unit ball of B is relatively compact in B weak. So relatively compact, it means that you know, the closure is compact, which is exactly what happened here in W11. This also is an exercise. You can prove that if you have a function that has the gradient that is bounded, a sequence of functions with the gradient that is uniformly bounded, then you can extract a convergent subsequence in L1. So that is what it says. Then the spectrum, the spectral radius of L is M, is bounded by M, and the essential spectrum, spectral radius of L, this is in B I'm talking about, is bounded by lambda M. Okay. So what does this mean in this case? In this case, it means the following, that in this case M is 1, so you have 1 here, okay? And we know that the spectrum of L as an operator from W11 to W11 must be bounded by 1, and the essential spectrum is contained in a disk of radius lambda, and which is smaller than 1, right? And so it means that outside there are only finitely many eigenvalues. Of course, this theorem doesn't tell you that the spectral radius is really 1. It could be smaller, but we just proved that there is an invariant measure. So there is an eigenvalue that has an eigenvector with eigenvalue 1. So 1 is indeed the point of the spectrum. So the spectral radius is exactly 1, because you have an upper bound, and you know that there is an element of the spectrum at 1. So this is what it looks like. Then if you want, you can, in this particular case of smooth expanding map, you can show that there are no other eigenvalue on the unit circle. That is, you have to use some geometric argument to prove that. It's not so hard, because essentially what happens is that if you have a well, yeah, in one dimension is easy, in higher dimension is a little bit more complicated, but essentially in one dimension, if you have a function that is in W11, then this function is continuous. So if you have an eigenvalue which is continuous, then it is different from 0 in some open set. This is not true in higher dimension. So in higher dimension, you have to do a slightly refined argument. But so if you have a function that is continuous in an open set, then you can iterate it and then it will be continuous in a bigger set. And so if you take an open set, you iterate it, it will just go over everything. So it cannot be that there is an invariant set that is contained an open set as is not everything. So that implies that there cannot be other eigenvalue on the unit circle. And if there are no other eigenvalue on the unit circle, since there are only finitely many eigenvalue outside here, then if there is another eigenvalue that is big, the biggest one will be away from the unit circle. So there will be a spectral gap. So that means that you can take your operator L and you can write it as L equal pi, where this is a rank 1 projector plus Q. Okay, so this is rank 1. It has actually, you know what it is in this case, right? Because you know that there is only one invariant measure, which is absolutely continuous with respect to Lebesgue now. So if you apply this to a function g, this is nothing else than this invariant measure times the integral of g. So that is what this rank 1 projector looks like. And this is the spectral decomposition. Here there is the rest of the spectrum. All the spectrum, there is one, and all the rest is contained in the disk that is strictly smaller than 1. You don't know exactly what this disk is because, I mean, you don't know what is the second eigenvalue. Maybe there is none, and then it will be this one, or maybe there is something. That depends from case to case. But in general, the point is that this operator Qn has a spectral radius that is smaller than 1. So it means that if you look at this norm, this will be smaller than something times some alpha n with alpha strictly smaller than 1. And this is a lot of information, because if you go back to, I erased it. Yes, I erased it. Fine. Let me erase this then again. It's anion stuff. And so, by the way, I mean, the thing that I'm saying, I mean, you can find them in many books, but I mean, there is a book that I wrote, lecture note that I wrote recently with Mark Demmer and Nilofar Chiamari. You find it on my webpage. So there you can find them, you know, this stuff if you want. I mean, the detail, right? I mean, because I'm skipping, I mean, okay, I mean, I had the choice, right? I could just do a few things with all details and bore you to death, or do fewer things, but skipping the details and trying to convey only the basic ideas. And that is what I decided to do. And maybe like that, you don't understand what I'm talking about, but I mean, there's a trade, the balance between these two things. So, okay, so the point is that what I wanted, I was interested in this thing, right? That's what I was interested in. And my idea, well, not mine, I'm sorry. I mean, this is just, I mean, the idea that people developed was to study this object. And now you know that it is, I mean, the fact that, I mean, there are other properties, right? Pi Q is equal Q pi is equal 0, because this is a spectral decomposition. So they have this property over there. And so it means that you can take power of L, and power of L will always look like phi, and then you have pi plus Qn G. Okay, and now this, you know what this looks like. So this is going to be equal to the integral of phi h star times the integral of g plus, and then you have this part here. But this part here, if, of course, if g belongs to W11, because if you are so crazy to take a g that is absurd, then you cannot say anything, right? So this actually, I should if someone you is used to similar problem in probability, then essentially a lot of the things that I'm going to discuss, they have a very close analogy in probability theory. Actually, they are actually copied from probability theory. I mean, that's what most of people in dynamical system, me included, do. They just study book in probability and they say, okay, this is nice theorem. Now let me copy it in the case of dynamical system. But by no chance, no. I said before that all this business was in some sense started by Kolmogorov, and Kolmogorov essentially axiomatized probability. So I mean, that's not a chance. It started like that. So but there is a caveat in probability. Normally, when you have not always, but in many cases, you just need to study observables that are in L2. So you have a measure, the observables that are in L2, and then you get, for example, exponential decay of correlation. In dynamical system, if you are using only L2 observable, you will not get anything. I mean, decay of correlation can be as small as you want, as low as you want. So that is a big difference that there is between probability and probabilistic argument and dynamical system argument. And the problem is that in probability, you start from an initial condition and then you jump somewhere, but there is some randomness, right? So immediately you are distributed somewhat in some way. But in deterministic system, if I start at a point, then my trajectory is fixed forever. So there is no randomness whatsoever. So if I start with some lack of knowledge about my initial conditions, then I can hope to see something that's spread around. And knowledge about initial condition has to do with how concentrated this function G is. Because if this is a delta function on a point, then it means that I start from a certain point. And then I will go somewhere, whatever it is, but I will never see some kind of probabilistic behavior. So I see a probabilistic behavior only because the measure I started with is not a delta function. It's far away from a delta function. And how do I ensure that a function is far away from a delta function? Well, I have to have control on some derivative. If I know that the function is as a derivative that is bounded by something, then of course it cannot be a delta function, because delta function, they have infinite derivative, obviously, like in some sense. I mean, it's the distributional sense. So, and that is exactly what this equality ensures. So it ensures that if I start with something that has bounded derivative, the derivative stays bounded forever. Bounded in this L1 sense. So that means that I can study this quantity, but only if this guy is in W11 in this case. And this guy here instead, this guy can be, well, you can compute. I mean, if it is in L infinity, that's okay, right? It can be a little bit worse because thinking in W11, I mean, if you are in one dimension, if you are in W11, then you are continuous. So you are in L infinity. So this guy can be in L1 and things are okay. But if you are in higher dimension, then you have to compute a little bit, because being in W11 means that you are in some LP, and then that it will be in the corresponding LQ, whatever. But this is just subtlety. But let's say that phi is in L infinity to make things easier, and then this thing is going to be order of nu to the n. So it means that you have that this stuff is converging to the invariant measure at an exponential rate. And that is a very nice information about what happened in this system. Okay. So I see that I'm going much slower than I thought. So, okay, that's what it is. Okay, so let me just take the point of view that whatever I say, and when the time is finished, I finish. What can I do? All right, so Of course, just to go back to something that was said this morning, so Caroline said, well, we like Lebesgue. Yes, I mean, I also like Lebesgue, but sometimes I don't. I mean, it depends. I'm not completely sure that Lebesgue is the only measure to consider. And so one may ask, well, okay, fine, but can I, like that, I can get the unique measure that is invariant and absolutely continuous with respect to Lebesgue. Can I get some other measures? And the answer is actually yes, you can get a huge class of measures just considering different transfer operators. For example, you can consider a transfer operator of this type. Sorry. I want to write the formula. No, I don't want the determinant. I want to write it like this. It was okay. I'm sorry, I start to be a little bit tired, so I write stupidity. Okay, so now you have this is just a different operator. If you make the choice phi equal the logarithm of the determinant of the map, then you get this guy over there. Where I erased it. I erased it. Okay, it's not written anymore. Well, okay, maybe you remember it, right? I mean, the case that I had before, it was phi equal minus the logarithm of the determinant of dt. Okay, you choose that, which is okay because this guy, as I said, is never zero, so that's perfectly good function, and he says this would be a C1 function. Okay, and so you do that, and you take phi C1, and you construct this operator. It's not the most general operator that you can construct. Why? Well, because essentially the exponential, first of all, phi is, in this case, I think about phi real. And in certain cases, it's important to consider phi complex. You may wonder why. Well, I mean, I will tell you later on. But phi complex, they play an important role. And another thing, even considering it real, then this guy is always positive. So, for example, if you want to put a hole in your system, you want to say that when you get to a certain place, you disappear, then you cannot write, you can still write a transfer operator, but it will not look like this. There will be a characteristic function. So if you want to put a characteristic function here, you cannot write it like that. Well, unless to say that phi is minus infinity. But then if phi is minus infinity, it's not going to be C1, right? So that is a limitation. It is important to study also this type of operators. They have a lot of interest in the theory. But again, I mean, I'm just giving you idea in the simplest possible case. So this is the simplest possible case. Okay. And again, you can play with this operator exactly as I did before. You can just take the derivative, and you will see that things do work. Because if you take the derivative, you will have the derivative of this will give you the derivative. One term will be the derivative of this, but against h. So it will give you a term of this form. And the other term will be the derivative of h. But the derivative of h will be multiplied as before by the inverse. And so you will get a contraction. So for this operator, you will get again the Lazotta-York inequality. As you do the same computation, you get the Lazotta-York inequality. And so, but the problem is that now you are not any longer a contraction in L1. Because this guy is something, right? It's not. Before it was a contraction in L1 because that weight was, so this is called these things, this is called the potential, and this is called the weight. The potential is phi, and the weight is e to the phi. So this language comes from statistical mechanics, and the reason was that you know, the second wave of people studying dynamical system, as you probably know, were people like Ruel, David Ruel, and Sinai, and they were people that were very knowledgeable about statistical mechanics. So they imported into dynamical system a lot of tools and language and ideas from statistical mechanics. And this, in fact, is a transfer operator in statistical mechanics is copied from there. Okay, so in some sense, this has been this statistical mechanical point of view is very apparent if you code the system using a Markov partition, which I will not talk about, but it is kind of convenient, if possible, not to use Markov partition, and then this connection with statistical mechanics kind of becomes less clear, but is still there. I mean, that is, these objects were invented over there. And so what? So still you can show that there is a spectral gap. It takes a little bit more. So you just can show that there is some alpha, which is some H star, which is, and this is, so the spectrum now becomes this. There is some alpha, and then there is the rest of the spectrum. Okay, so you can prove more or less the same as before. It takes a little bit more work, but that's essentially what you can do. And you can say, okay, fine. And so what? I mean, but before it was clear, right, what to do, because it had, I mean, I was constructing measures, right? But now this eigenvalue, before the eigenvalue was the density of a measure, but now what is it exactly? I have no idea. So what it is indeed? What time is it? Yes. So the point is that L phi now we'll have again a decomposition, which will be alpha, which is the biggest eigenvalue. Then there will be H star. Then there will be some L. So if I apply it to G, then there will be some L of G plus Q of G. As before, this guy belongs to W11. This guy is in the dual of W11, because acts on element of W11, so belongs to the dual. And this guy instead has a spectral radius which is bounded by some beta time to the Henson constant, where beta is smaller than half. So that is exactly as before. The only thing is that you are a little bit unhappy, right? Because what's the dual of W11? What the hell is that? I mean, it looks not so nice, but you know what? Remember that L is a positive operator. So if you have that G is positive, this implies that L phi G is positive. And this means that if you look at L and G, this of X, this is equal to H star X, L G plus, and then you have Q and G. Okay. And so you can write, you can put this on this side, Oh, sorry. I want to divide by alpha to the minus n, sorry. So this is alpha to the minus n. P. Yes? When I iterate L to the n is alpha to the n times this stuff. This has L of H star is 1. That is the normalization that you have. Yes. This is a projector, right? That must be a projector. So if it is a projector, if you apply to itself, must be itself. So it must be that L of H star is equal to 1. That's how it is normalized. Okay. And so if you normalize it by alpha minus 1, then you get this thing, right? But the point is that this is positive. So I put this on the other side. And then you get that this is positive and this goes to 0. Okay, so in the limit, I have that LG must be positive. This is positive too, because it's obtained by iteration of positive things. You can obtain this by Krylov-Bogolyubov as before, just considering the average of alpha minus k L phi to the k of some fun of 1, for example, sum for k from 1 to infinity, 1, n minus 1, 0, 1 over n. Okay, this will converge to H star. If you, will converge to A star times L of 1. Okay. But since this is positive, this must be positive. So L of 1 must be positive. And this guy is positive again, right? And that is the same argument as before, because this does not grow now. And so this is positive, but so this is the distribution, right? But positive distribution are measures. So this is a measure. So this implies that L is a measure. Okay. So it's not just a weird object that is in some element of the dual of W11 that could be some idiotic distribution, like the derivative of the delta function or something like that. It is a measure. And so now that you know that, situation is quite nice because you can construct a new measure. This trick is kind of, I always find it amazing, but it works. And this, you construct the measure mu of phi equal L of phi h, okay? And now let's say that phi is C0. No, C0 maybe is, let's say C1. Is C1, okay? And now you write this thing, you see, in general, it's dangerous, right? Because, okay, you have to make sure that what you write makes sense. But this is in the dual of L1 of W11. If you take an element of W11 and you multiply it by a C1 function, this is in W11. And since this is in the dual, this is perfectly okay. I mean, so it's kind of that you don't even need to know that it's a measure. It's okay anyhow. This is useful that because sometimes it's not a measure in more general situations. Okay, so now you have this, and you can say, okay, I construct this object here. Okay, this is a measure because this is a measure. I know it's a measure, so this is a measure also. And you can say, okay, fine. So what about this measure? Well, what about this measure? Let's see. Let's look at mu of phi composed T. This one is equal to L of phi h composed T. Okay. This is like saying, sorry, H star. This is H star. This is like L of phi composed T H star. And then I can put L phi here, alpha minus 1. Why? Well, because L is the left eigenvalue of this guy. Just out of the spectral decomposition, it follows that if I have any function G and I have L phi of G, this is equal to alpha L of G. Okay, so if I multiply by alpha minus 1, I can do that. And now this is a sum on preimages, but this is composed with T. So if I take the preimage and then I take the image, I get the point that I started with. So this is equal to alpha minus 1 L of phi L phi H star. But this is an eigenvalue. So this is alpha for that, and so this is alpha phi H star. But this is mu of phi. So that is an invariant measure. So we just constructed an invariant measure out of this operator L phi. For each phi that you choose, you produce an invariant measure. So this is a machinery that produce bazillion of invariant measures for you. These are called Gibbs measures, by the way. Produce a bazillion of these invariant measures, and they are all, I mean, in this case, they are kind of unique. For each phi, this is not always the case, but in this case, for each phi, you have a, sorry, because I don't know, 27, 3 minutes. For each phi, you produce one invariant measure. And it's easy to do the contrary. If you have an invariant measure in certain, which is an invariant measure, you can construct an operator that produce it, if it is in some class, if it is a Gibbs measure. I mean, there are some conditions, right? Okay, so that's kind of a nice machinery. And just let me, in the last 3 minutes, let me just tell you that there is kind of some further stories that come from statistical mechanics that are variational principles. I'm not going to talk about them, but let's just me kind of allure you, just telling you some nice case. Consider the case phi equals 0. This is the most stupid potential you can ever choose. It means that the transfer operator just makes a sum on the preimages. That's all what it does. Okay. And in this case, you may wonder, so if you have an expanding map of the torus to itself, then how many preimages you have is simply the degree of the map. So let's say that T has degree D. That means that if I take L of 1, phi 0 in this case, because phi is 0 in my case, then this is simply going to be equal to the preimages of X of 1. So I just count the preimages, and so I get D. And this is D times 1. So I have explicitly my H star is 1 in this case. The eigenvector is simply 1, and the eigenvalue is D. It's totally stupid, right? But there is something that is interesting, which is what is the topological entropy here. So the topological entropy is defined as, so you say that A is an n epsilon, what is it called? I never remember. I wrote it because I always forget. It is an n spanning set if you take the union for the X that belongs to A of the dynamical ball center in X and radius epsilon. What is a dynamical ball? Dynamical ball is a ball in the dynamical distance. So it means that this is the set of the X, of the Y, such that the sup for k that goes from 0 to n of the distance between f k x f k y is smaller than epsilon. Because that is the dynamical ball of order n. It means that the trajectory for n step, they stay epsilon close. Okay? Point in the ball, if you go in the future, they stay epsilon close for n step. And so, sorry, I didn't say if this is equal to everything, in this case, TD. Okay, so you cover with balls, you cover the full space, and you just take the cardinality of A, which is, and then you take the inf essentially, right, of A n epsilon spanning. Then you take the logarithm, that you take 1 over n, you take the limit for n going to infinity, you take the limit for epsilon going to 0, and this is the topological entropy of T by definition. Okay. And now it's not so difficult to compute in this case what is an epsilon spanning set, because if you want to stay together for n times, then it means that you take the space and then you take the preimages for n times. If you take the n time preimage of the space, you will get a lot of balls essentially, right? And the point must be a dynamical ball must be in the preimage, because if it is not, if 2 points are not in the same n preimage, then at a certain point they will be at the distance 1, not at the distance epsilon, because you have this is T2. Well, I mean, this kind of imaginary, and then the preimage will be, something like that. I mean, each one of these will be all the space and so on and so forth. But if you take a point here and a point here, then they can be anywhere, right? So that means that essentially an epsilon spanning set, this cardinality here is going to be essentially epsilon minus d. Sorry, epsilon, no, degree minus the dimension. Oh, d. I use d for too many things. I'm sorry. Yeah, I mean, let's say this is m. Okay, Tm, and that is d, is the degree. So this will be minus m time d to the n, because I have this many preimages, d to the n preimages of the full space, and so the balls must be contained there. Each ball more or less is preimage. I mean, the full space I can cover it with epsilon minus m ball. I cannot do much better than that. And so now you have to take the logarithm, and you take so the logarithm will be just the logarithm of this plus n, the logarithm of d, and then you divide by n, you take the limit, and you get the logarithm of d. So that means that the topological entropy is the logarithm of the degree. And so it means that this is E to the topological entropy. So, and the topological entropy is the soup of all the possible measured theoretical entropies. So there is some kind of variational principle that the eigenvalue, the maximal eigenvalue, is given by the soup over all the metric entropy of the map. And this generalized to some more general variational principle in which this is the pressure of the potential field. And the pressure of 1, the pressure of 0 is just the topological entropy, but more in general. But anyhow, this thing You can find it in books, for example, in the books by Vivian Valadi are nicely explained if you want to know more. But this was just to give you a taste of the fact that the maximal eigenvalue has some interpretation that it is interesting by itself. For example, this shows that the measure mu is the measure of maximal entropy of the system, which is kind of nice. Sometimes you want to know the measure of maximal entropy, and this is an answer in this case. So I think I stop here. I think I went over time. 6 minutes over time. Apologies. You should have stopped me. You are the boss. I mean, I'm sorry.
So I was also uncertain about what approach to take to the seminar, if I'm making more introductive or not. So I will do a little bit like maybe like Carlangelo did. I will make a survey of something and with trying to focus on ideas. But however, I will focus on algorithms, and for the rigorous, we will specify what I mean by rigorous computation of things related to the statistical properties of dynamics, and in particular about invariant measures, as we have seen in the last talk. And not only invariant measure, maybe the second important topic will be how to estimate the speed of convergence to equilibrium, which is related to the decay of correlation, and it is related to what we have seen in the previous seminar. And not only this, I will also say something about how to about the fact that this algorithm can be also implemented in a careful way, in a way that you can keep track of all the rounding errors that you make making a lot of calculations, like we have seen in this morning in the lecture of this morning. And so if you have some algorithm that in principle can give you an explicit bound on on something that you want to approximate, and the algorithm can give you an explicit bound for the approximation error, and then you implement the algorithm with this kind of implementation, which you keep track of all the possible rounding errors, then at the end, the output of the computation will have some mathematical meaning, and it will be useful to prove something and to make some computer-aided proof. I will give an example of this. So I'm very lucky that I have not to repeat what is a transfer operator and so on. But the point of view that we will take about dynamical systems and invariant measure will be that we are going to consider certain, just to start, let's say, a deterministic dynamical system. We will consider the associated transfer operator, the transfer operator associated to the dynamical system. Here, the notation is a little bit different from the previous lecture, because here I'm denoting as a transfer operator already the map induced at the level of probability measures, or measure with sign, while before we have denoted these by T star, and we said that the transfer operator is the action of these, but at the level of densities. Now, in this notation, I take the action of the map at the level of measures, but then we will almost always talk about measure having a density, so it's the same thing. At the end, it's the same thing. And we want to talk about invariant measures, so finding, in some sense, algorithms to find fixed point for this transfer operator. Of course, looking to the transfer operator acting on probabilities will include a lot of invariant measures that we are not interested to see. And as we have seen today several times. One is interested to look to some special measure having a physical meaning. And among the very nice thing that these physical measures have is that they are several times also the most regular ones among the invariant measures. So it's a good idea to search for an interesting invariant measure inside some space of regular measure. And we have to find the good space of regular measure where we will find the physically interesting one. We will talk about how to find the fixed point in spaces of measures, and also how to measure the speed of convergence to the limit when you start from a certain measure which is different from the invariant one. Maybe this will be an absolutely continuous invariant measure, and then you iterate, and we know that if the system has convergence to equilibrium, the iterate will converge to the invariant measure, and we will want to measure the speed of this convergence in an algorithmic way, in the sense that if someone give me the dynamical system and the starting measure, I can say, I make some computation and I say, okay, if you iterate, let's say 20 times, then the distance from the measure that you give me and the invariant measure is smaller than this in some distance, distance that you choose in your space of measure that you want to consider. So let's precise a little bit what, so let's start talking about computing invariant measure. What I mean by to compute a measure, what the idea is that the measure, we see the measure as an element of a metric space. We want to compute to give an approximation, and which will be another point of the metric space, and we want to be certain that the approximated measure that we have computed is near to the real one, according to the distance that we have chosen. For example, a simple distance that we can put on a space of probability measure is this one, is the dual of Lipschitz. This is a kind of Wasserstein distance, and maybe we want to approximate some invariant measure with this distance, or maybe we are interested in absolutely continuous measure, and then we choose the L1 distance, and so on and so on. And by rigorously approximating a certain measure, I will mean to give something approximating it up to some error which can be computed explicitly. So I can say, oh, look, this is an approximation which is a distance less than 1/100, or this one is a distance which is less than 1/1000, and so on and so on. And we would like to be able to make the error as small as wanted, but at least to have an explicit estimate for the error. So I can say, my approximation has a mathematical meaning. I can say I can do something with this. When I know what is the approximating measure and what is the distance between the approximating one and the real one. And we would like to also make this feasible on a computer, because we will see this computation will involve a lot of operation to be done. So before to start, let me say an abstract result. Some time ago, I was trying with Hoyrup and Rojas to prove something abstract like this. We wanted to prove that a computable dynamical system always should have a computable invariant measure, or maybe a computable physical invariant measure, what I mean by computable for the system and for the measure is what I was saying before. A computable dynamical system is a system. I will not give a precise definition for this, but if someone is interested, I can show later. But a computable dynamical system is a system for which the map is, you can approximate where every point go by an algorithm. The map is approximable by an algorithm at any given approximation. So there is an algorithm that represents the map. So we wanted to try to prove that there is also a computable invariant measure. That is a measure for which there is an algorithm showing approximation which are better and better and better. In some sense, it is a way to compute the invariant measure. But while we were trying to prove this theorem, we convinced ourselves that it was wrong. It was false. And we found an example of a system which is computable. And this system has a lot of invariant measures, but none of them is computable. So it's something quite strong, because a first question would be, is there a computable invariant measure? A second question would be, is there an algorithm to go from the code for the map to the code for the measure? This is quite a bad example, because it shows that even the first question is not true. There are systems which are, in some sense, simple from the computational point of view, but there are no computable invariant measures. So it means that there is some subtlety in this problem in general, but from now on, we will not take this problem at this level of abstraction. We want to try to write down some algorithm and run some program to make. It's a bit complicated, but it's an example in which you have a lot of fixed points, but is a set of fixed points, and this set attracts everything. But let's say the way in which all the space is attracted is on the circle, if I remember well. The speed is lower than any computable function, and so there are a lot of semi-computable invariant measure, because if you follow one point, it will go to a fixed point eventually, but you don't have a way to know by an algorithm how fast he is going. But I forgot a little bit all the example. I know that Cristobal and Mathieu, they have some recent result for some even worse example, but I cannot say exactly how it works. It was about Bratelli diagrams. I don't know if you have ever heard. Okay, but this was like just to say that there is some subtlety, some abstract subtlety, but now we want to go to the concrete situation on which we want to get a system and try to run some program. So one idea, which is a good idea, is that since we have seen that we can associate to the system a linear operator on some Banach space, one idea is, okay, why don't we approximate the linear operator, which is an infinite dimensional operator, with something which is a finite dimensional, and then approximate the fixed point that we want to compute with the fixed point of this, because if this is a finite rank, it will be a matrix, and then we put it in the computer, and the computer is able to compute. This will be a kind of finite element approach for the problem, but of course, if you do like this, if this is your idea, you have to have some way to estimate in some sense the distance from the fixed point from the distance of the operator or something like this. And this will be a kind of stability result for the fixed point of the fixed points of operators. Let me describe maybe the simplest way in which you can do this finite element reduction, which is the Ulam method, the so-called Ulam method. In this method, what you do is you take your phase space, you consider a partition on your phase space, so the space will be discretized by the element of this partition, and by this partition you define a finite rank projection, sending a generic measure with sign to a special L1 function, which will be constant on every piece of the partition. And you can do this by considering the conditional expectation of the measure with respect to the partition. So, and here you define, suppose we call the partition I delta. Delta will be a kind of size of the mesh. It will be, if you take delta very small, it will be a very fine partition. If you take large, you have a few pieces. And so for every delta, you can define a projection of this kind. So from, for example, this will be a measure having a density F, and the result will be something like this, a piecewise constant function. So if you use this projection, you can find a finite rank version of your transfer operator in this way. You compose the operator by the projection before and after. So any measure you put here will be transformed into an histogram, then you apply the transfer operator, then you transform again, because of course after applying the transfer operator to an histogram, an histogram, I said histogram, maybe, I don't know, then it's not an histogram anymore, but then you apply the projection again. So you get back to your finite dimensional space again. So this will be our approximation for the transfer operator. And with some work and understanding, you understand that since you are, in this case, the transfer operators are Markov operator, then what you are doing, this new approximated operator is the transition matrix of a finite state Markov chain. So essentially, in the Ulam method, what you do is to approximate your system with a finite state Markov chain. And then the question is, if delta goes to 0, the measure that the fixed point of the Markov chain will converge to the invariant measure of the system, which invariant measure, and so on and so on. About these kind of questions, there are a lot of results in the literature. Our point of view is to find a suitable assumption for which we can not only say that the measure, the approximation converge, but we can give explicit bounds on the approximation error. Of course, let me say there will be no time to talk about this, but this Ulam discretization, that is approximating any function or any measure with piecewise constant function, is one idea, but you can do and try to apply other approximation schemes by polynomials, by Taylor polynomials maybe, or by Fourier analysis, or by piecewise linear functions, and so on and so on. And every one of these approximation schemes will be suitable maybe for classes of systems. For example, if I don't know. Maybe Caroline knows, or yes. Yes, yes, it's an idea. If you have a reason to do it, let's do it. I mean, a system for which this work. The approximation scheme should depend on the system. If you have a lot of smoothness, probably approximating by smooth function is better than approximating by piecewise constant function. And the rate of approximation are much faster and better, and so on and so on. While on the other side, if you have in some kind of system, you better approximate with some in a weaker topology, for example, with delta functions, or in the Wasserstein distance, or maybe, as now is well known, if you have both contracting and expanding direction, you will be led to define some anisotropic space in which you have some weak norm in the contracting direction and some strong norm in the expanding one, and so on and so on. And then you will find a space of distribution to which you want to use to approximate everything. However, all these ideas are based on some projection, phi, which is finite dimensional. These are not the only ideas that came in the literature for the approximation of invariant measure. There are other ideas, but for this talk, I want to restrict to the finite rank approximation given by a certain projection. How to estimate the distance of the fixed point from the operator and the approximation? Now I will show this simple result that we found useful for the implementation and for the algorithm. By the way, this result came after a discussion with Carlangelo long time ago. I don't know if you remember in Rome. Well, okay. The general framework is the framework that we have seen before. We let the transfer operator to act on a weaker and a stronger space. So suppose that now we restrict our transfer operator to some strong space. This could be like the Sobolev space, and also to a weak one. It could be, for example, L1. And suppose the following things. Suppose that we have two operators. This will be the real operator, and this will be the approximated operator. But this is true, like in general, for Markov operator between these spaces. So this is not forced to be the Ulam approximation. This is some operator and some Markov operator. Suppose that you want to consider this space. V will be the space of measure having zero average. We know that the convergence to equilibrium is related to the contraction of the space. And suppose that the two operators are near each other in a mixed norm. This is the mixed norm. It will be the norm of the difference of this linear operator, considered as an operator from the strong norm, the strong topology to the weak topology. And suppose that you can find some n such that when you iterate n time the approximated operator on the space of zero average measure, you get a contraction which is better than 1/2. This is arbitrary. You can take another number, but let's take 1/2. Suppose that if you iterate enough, then you have a contraction on the weak norm that is better than 1/2, and call Ci the norms of the iterate of this operator restricted to the zero average space from 1 to n, then the distance between the fixed points, between the fixed probability measure, I have not only to say fixed point because you can renormalize. So we renormalize to probability measure. So the distance between f delta and f is smaller than 2, the distance between the operator, the strong norm of f, and a sum, which is a finite sum from 0 to n minus 1 of this Ci. So essentially, once you find this n, you compute the Ci, and this will be a number. Now, I don't think this result is optimal because this is from the week to the week, but it was very comfortable and useful for the computation. Because why? The point of the use of the result is that we are asking, the hard part here is computing this n, and this n will be computed by the computer, because this is the approximating operator. So this will be a matrix. So when I set up the problem, I will define my approximation scheme. So it will be not very hard to compute this one once I decide delta. This one will be computed by the computer. The computer will compute a big matrix, and then we start with iterating and until he finds a norm which is smaller than 1/2. And usually computing a weak norm of a matrix is quite simple. For the L1 norm is very simple. So it will be not expensive. And then starting from these two numbers, you have an estimate for the error. This is what we then call the a posteriori estimate, because in many approaches to the rigorous computation of invariant measure, in some place you need some estimate for some convergence to equilibrium. But if you want to give estimates for the convergence to equilibrium of transfer operator, which are explicit with explicit bound, it can be sometimes technically complicated. And instead, in this approach, you don't need to estimate this for the real transfer operator. You need this for the approximated one. So it's a matrix. You ask the computer, and the computer will answer you. Okay. This is thank you for asking, because this is an important point. This estimate doesn't say that you will be able to make this error as small as you want. This estimate, indeed, is a posteriori one. You choose your delta, you hope that it will give you a small error. Then you start all the computation. The computer will compute this, and if this is not too bad, then at the end you will have a small error. In fact, for some classes of system a posteriori, let's say, you can also prove that this can be made as small as you want for systems satisfying Alazoth-York inequality, and so on and so on and so on. But in general, from only this result, you cannot say. But the good thing is that here you need only a few assumptions, and you can try. For example, we will see that we can apply this to intermittent system, which has no spectral gap, and so on and so on. And it works just because of luck, not so much because it works. But in some cases it may not work. So let me explain a little. One more question. This I was saying. This is another thing that I have to explain. Someone can ask, but how can you compute this this strong norm if you don't know who is F. But how to get information on the regularity of invariant measure is something that we have seen in the previous lecture. For example, by the Lasota-York inequality, we have seen that even if we don't know what is the invariant measure, we can have an estimate from the coefficients of the Lasota-York inequality. You can have an estimate for this norm. Okay, so this is why the application is possible. So this is a posteriori estimate because you ask the computer to compute the speed of convergence to equilibrium, and you can have this bound from something like Lasota-York inequality, or maybe to some other idea like cons which are preserved or something like this. This, for example, is what we have done for the Mandeville-Pomeau-like maps. Okay, now let me just add that, but this is something that we have seen also before, something that people like to compute when they compute invariant measures. In one dimension, they always want to compute Lyapunov exponents. And we have seen before that computing that the Lyapunov exponent is equivalent to get the average of this observable. Maybe here we should need the absolute value, but okay, more or less this is the idea, is the average of an observable. And now let me show some example where this we were able to apply this very simple result. The simplest case is one-dimensional expanding or piecewise expanding map. This is an example in which you have a Lorentz-like map because there are unbounded derivatives here and here. This is not continuous, so it is piecewise expanding. And this is a plot of the invariant measure that we can compute with this number of intervals. And of course, I cannot give all the values for the histogram, but this is just a plot. But we can prove that the error that we make is that small. Now we can do much better. This is like an old result. And for example, for this case and for this partition, you have to wait 7 iterates to contract better than 1/2. Another example, as I was saying, is a intermittent map, a Mandeville-Pomeau-like map. This is a much more complicated example because there is no Lasota-York inequality to help you, but still you can find the invariant sets from which you can find estimates for the regularity of the invariant measure. And here, as you can expect, you need much more iteration. We take this partition, so it's quite fine. However, once you take the partition and you compute the matrix, this will be a Markov chain, which has exponential convergence to equilibrium. So if you are lucky, maybe it's not so slow. And what we found in this computation is that with 50 iterates, this contract better than 1/2. And then you can try to compute the error, which at the end is not very large also. And of course, now there are more precise, yes, this is a graph of the map with the fixed point, which is not expanding. And this is a picture of the invariant measure. Of course, this is unbounded, but you don't see in the average on you this small piece of the histogram will be the average of the unbounded density in the first very small interval. But probably this plot has not the same resolution as this. It's just a plot. But if you could plot the real plot with all these 1 million of elements, there will be a first histogram, and the height of this histogram is the average. Yeah, yes, me too. It's like that. You see, here there is still quite enough density, but it is like this. But however, now there are new results and much better approximations. So this is just to say, with this simple, stupid result, you can do many different things. And I'm showing which things. Then if you do more complicated things, of course, you get better and better approximation.
The map had a different fixed point.
Yes.
And one would expect
only here.
Yes, one would expect some density.
This is integrable because this exponent is small.
Okay.
There is a range in which the density is unbounded but still integrable, and then over this range you start to be outside the integrable part. This is integrable unless everything will be much more complicated. Okay, another example where you can apply the stupid result is iterated function systems. This is a random system on the square for which you compose randomly some linear map, and this is a plot of the invariant measure that you get, and this is let's say the error that we can certify in the Wasserstein distance here. Okay, let me, I don't know how much time I'm spending in this, but let me go a little bit faster. This, again, we could also apply to systems which are piecewise hyperbolics, but simple. This is a simple map, which is a skew product map, which is piecewise hyperbolic, and it is related to the famous Lorentz system. The actual map that we have considered is this one, but the behavior of this map is to plot this is a map on the square. This is S plus, this is the image of S plus, and this is S minus, and this is the image of S minus. So this map is stretching, but with some discontinuity in the horizontal direction and contracting in the vertical direction, with a lot of contraction here and here. This is a Lorentz like two-dimensional map, and this is a plot of the invariant measure. This is a zoom that if you zoom, you start to see the fractal behavior of the measure, and the different colors are different densities that you have, and then we can certify an error again in the Wasserstein distance. And of course, from the knowledge of the measure and of the distance, you can also compute an estimate for the dimension for this. Yes. Yes. Yes, but here the thing that we have done is the real thing that we have done is only a part of this is an application of the result that I was saying. To speed up the process, what we have done is, since this is a skew product map, so we approximate the invariant measure for the base map, which is a piecewise expanding map. Then we compute how many times we have to iterate the contracting part to contract enough. And then we not exactly this. Is used in the first part. The second part was just iterating every vertical direction. Yes, and this is the real topic of this talk. So, next example is an example in which we have made a computer-aided proof on a system in which we needed to iterate a priori, we should iterate matrices of like 10 millions of columns. So we had to find a way to avoid to iterate these huge matrices. I don't know how much time I have to motivate this, but okay, let me try. This is I try to motivate more because this is an interesting. This problem has a long story. It starts with the famous Belousov-Zhabotinsky chemical reaction, which was a big discovery in chemistry, because this is a chemical reaction having a chaotic behavior in some sense. And by the way, for these poor guys, it took 20 years to publish the paper. There is an interesting story about this, because nobody wanted to believe that a chemical reaction could be chaotic, because everybody was thinking that everything should go to the thermodynamic equilibrium fast enough, and so nobody used to believe, but it took a lot of time. So after the community accepted their discovery, of course, there was a lot of people trying to study why this strange thing is happening, and a lot of models were produced. And studying numerically one of these models, these two guys, Matsumoto and Suda, discovered a strange phenomenon that they called noise-induced order. The phenomenon is like this. The model I will show in the next slide is a one-dimensional map plus additive noise. They tried to add more or less noise, because it's not clear how much noise you should put in the very simplified mathematical model. This is like the Lorentz ODE as a model of the weather. This is a complex system in which people try to simplify. You arrive to one-dimensional map, but you have to put some noise. So they tried to make experiment with more or less noise, and they discovered that with more noise, the system was less chaotic. With a lot of noise, the system had negative Lyapunov exponent, and with small noise, the system had positive Lyapunov exponent. So for them, it was something strange. They called the noise-induced order. And indeed, it was a topic that was studied a lot in the nonlinear science community. And then the phenomenon was found in many other kind of systems. As far as we know, there was no mathematical proof that what these Matsumoto and Suda discovered was something mathematically true. And we have done a computer-aided proof about this. So let me describe a little bit more the system. The system is I don't know, for many people, there is a difference. And for many people, the mathematically true is irrelevant. What is relevant is what is really true in the real life. Okay, but okay, we are mathematicians. For us, what is true is what is mathematically true. So it was a conjecture. And now we hope it is a theory. So, the model is made like this. There is a deterministic map, which is this one, which has a formula with some coefficients which have been written in the paper. And then you build a random system starting from this map, in which at every step you iterate the map, you apply the map, and then you add some uniformly distributed noise in a small interval with radius psi. So what you do is like this: you take a point, you apply the map, then you add a random quantity. No, there is. This is worse than a critical point. There is zero derivative on this side, and then there is an angle on the other side, because there is this is, and is different than zero, but because this is a piecewise defined formula, and there is also infinite derivative here and very small derivative here. There is, because this region is very contracting. So one idea is that if you put more invariant measure here, you kill the Lyapunov exponent easily. But you have to prove it. Why this is not easy to prove? Because as a deterministic system, this is a very bad system. We have seen this morning that already for logistic maps, the statements are very complicated and very hard to prove. This one, about this system, I have no idea if there is something that one can prove. But we are lucky because we don't need to consider the deterministic system alone. We always have noise. And the noise is always smoothing, maybe just a little bit because the noise is small. But it gives you at least some smoothing and some Lasota-York inequality in some sense. This is the system. This is the plot from the original paper. I put in green the 0. What they proved is that for small noise, you have positive Lyapunov exponent, then you have a transition, and then you have negative Lyapunov exponent. And this is what we tried to prove with a computer-aided proof. Yes, this is a figure taken from their paper. It is not perfectly clear what they computed, but because it's not explained in any detail, like how many orbits they took average on orbits. I don't know, but essentially people think that what they have computed is this. They simulate a lot of orbit, maybe they take some average, but they at the end they compute an estimate for the average of this observable by iterating orbit, of course. So since we have to estimate something like this, of course, it is possible by yes, this is another thing to discuss. How this is meaningful, this is yes, this is what they computed. But I think that the idea is that the dynamics is the system and the noise comes from outside. So if you start with two nearby initial conditions, then these conditions are separated only by the derivative of the map, because during their life, the noise will be the same for the two trajectories. So this is the interpretation I have. So this is a way to define a Lyapunov exponent for this kind of system. Yes, but the random system will be a little bit complicated because this is a random system with additive noise. So it will be I don't know. Let's discuss this later. I mean, I agree with you. This is something that is not clear what is the real meaning of this. My opinion on the real meaning of this is that the noise comes from outside. So you only can choose nearby initial condition in the deterministic part, and then you see how they are separated during the dynamics. But the orbits are not deterministic. They are also subjected to the noise. So this is my interpretation. What we can do probably we can define everything, but maybe there will be no transition. There will be no transition. Maybe yes, maybe not. I don't know. I don't know what will be the other case. We studied this case because this is what they have done. And let me say why we can do it. Because, of course, if you want to estimate this, if you have information on the measure, because this you have the formula for the map. And if you have an approximation of the measure, you can approximate the integral. It's not completely trivial because the observable is unbounded. So an L1 estimate on the measure is not enough to get everything, but you can make something a little bit more complicated and then arrive to prove something. And this is what we were able to prove by a computer-aided proof. We proved that there is a transition because we found sides for the noise for which the Lyapunov exponent is certified to be in this interval, which is positive, and another size for the noise, which is larger, and the Lyapunov exponent is certified to be in the negative interval. Of course, we didn't do the computation only for these two sizes for the noise. We did many, and this is the graph that we get. The upper arrow are the upper bounds on where the Lyapunov exponent is, and the lower arrow, the blue ones, are the lower bounds. As we see, for large size of the noise, we have very small errors, and for small sizes for the noise, we have larger error. This is intuitive because when you have large noise, the system is very smooth. So you need not a very complicated, very fine approximation. But when for this last computation, the situation was hard. We needed to get a very fine approximation, and so we needed to, in principle, to estimate the convergence to equilibrium for very, very large matrices. And here, but this one, so this is 0.1, this minus 0.6. This is still very small. No, not very small, quite small. And this graph corresponds to this part of the graph from the original paper. Is a little piece. We are not able to go too much near to the zero noise limit. Okay, but still we can see the transition, and the transition happened around 10 to the minus 4. So we needed to be able to see the behavior of system with this small noise. So doing this, let me see how much time still I have. Well, I think I talked for like 6 minutes, so I'm sorry. So I will go very fast. So this involved in principle, the iteration of very big matrices, but we didn't do this. We did not iterate with these 10 million columns matrices, but we consider this very big matrix again as transfer operator, abstract transfer operator, for which we want to compute the convergence to equilibrium by Coarser approximation. So we have a big matrix representing a system. Now, only for the convergence to equilibrium, we approximate the big matrix with a smaller matrix, which is a kind of coarser version of this. And how to do this? Let me say one thing in 1 minute. Now, the code for doing this kind of numerical approximation and computation of invariant measure are implemented in Julia, and there is a public release under the package Julia Dynamics, and so it will be quite easy to use. It's like this morning lecture notebooks, and indeed there are also Jupyter notebooks which we use to explain the code in a summer school. So here you can find the Jupyter notebooks with all the routines that you can apply to compute the several things. Of course, for the explanation of how to use it, there are video of the lecture, but the Hokkaido University doesn't want to make it public. So if someone is interested, please write me, and I will give you the password. Is on Vimeo with a restricted access. Okay, so you can see they should be quite simple to use. So let me, in like 3 minutes, say the basic of the idea. of this quartz-fine approximation. The idea is based on the following thing. The big matrix and the small matrix, they both satisfy Lasota-York inequality, and they are near in some sense. And for the small matrix, you can compute more easily the convergence to equilibrium. So we will suppose this. The big matrix is satisfying a Lasota-York inequality. The projection is like this, and the difference, I mean, the distance from the identity of the projection is bounded by a constant time delta, time. Yes, the big matrix is the fine approximation. This one? No, because if the discretization, you know what is the discretization, sometimes it is easy to prove that the discretized operator satisfies the same Lasota-York inequality as the original one. This is something, I'm talking about something in general, but if you want to apply this to the Belousov-Sapoti situation, the system satisfies a Lasota-York inequality because of the noise. Is a Lasota-York inequality with lambda 1, 0. Is the best one because the noise is regularizing from L1 to BV directly. Yes, 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 yes. And that's why you have, in principle, you have to iterate many times to see the contraction. And that's why it's complicated. That's why it's complicated. But then if you try to do, now I'm sorry, I probably have not the time to explain the method, but the method is about putting in a system of inequalities, because at the end you can prove an inequality for the iterate of your time field operator, the difference of the iterate of the real operator and the approximated one. And then if you put the Lasota-York inequality and an easy inequality that comes from the previous lemma, which is a bound on the iterate of the difference, you can replace this with something that can be computed by your computed on a coarser matrix. And then at the end, you have a vector inequality, and all the information is condensed into a small matrix. And at the end, you know that the iterate, the strong norm and the weak norm of the iterate of some initial measure are bounded in something by something like this. This is the iterates of a 2 by 2 matrix, which you can compute from all the estimate that you have in your system, Lasota-York inequality, and so on and so on. And by this, you can compute how small is this after you iterate n times. And by this, you can somewhat estimate the convergence to equilibrium of the larger matrix. I cannot explain better. Let me also skip these and the details and just show some comparison between the method without speeding up by the coarse-fine method and the method with the speed up from the coarse-fine method. By the way, what I'm saying now is included in the preprint that was published on arXiv yesterday. So, if you want to find the details are there. But for example, this is a piecewise map which is no Markov, and piecewise expanding map which is not Markov and not linear. We can have this much better approximation for the Lyapunov exponent by this two-grid method, and this is a comparison of the computation time for iterating the matrix without doing nothing or using the coarse fine method. And you see the speed up is quite important because here you arrive to 2 to the 15. 2 to the 15 is here. The vertical scale is the same. So this is the time for the old method. This is the time for the new method. This is quite a big improvement. And also we did with a smooth map, but with a piecewise linear approximation. So it's not the Ulam one, and we get similar results. So, so this is the preprint which was put yesterday, and I think I stop here. Let me only say that Federico Poloni is here, and he's so if someone, because one of my motivation for this seminar was to advertise a little bit this thing. We are trying to make a place where to put this kind of tools. So if someone is interested to contribute, we are very open. And, but I am not a programmer, so if you ask me, I don't know exactly what to do, but Federico is the expert here. So let us know. Thank you.